Hello there, fellow wanderer of the cosmos. Thank you for joining me tonight. We're about to embark on one of the most impossible journeys imaginable. We're going to explore what would happen if you could outrun light itself, the ultimate speed limit of the universe, the cosmic constant that governs everything from the smallest particle to the largest galaxy. Before we begin, I'm curious, where are you listening from right now? And what time is it where you are? I love imagining all the different places this story might find you. If you enjoy these gentle explorations into the mysteries of science, please consider liking this video. It helps others discover these quiet moments of wonder too. I should probably warn you that thinking about faster-than-light travel might cause temporary symptoms of existential awe, sudden urges to question the nature of reality, and possibly an overwhelming desire to become a theoretical physicist. Side effects may include vivid dreams about riding photons and an inexplicable need to explain relativity to your houseplants. So settle in comfortably. Let your breathing slow. Tonight, we're going to gently break the most fundamental law of physics and see what happens when we leave light itself in the dust. The universe has some very strong opinions about this, but we're going to explore them together. Imagine, if you will, that you're holding a cosmic speed limit sign, not the kind you see on highways, but one that applies to everything in the universe, every particle, every wave, every piece of information. This sign reads 299,792,458 meters per second. This isn't just fast. Fast is a racing car or a jet plane. This is something entirely different. Light doesn't just happen to travel at this speed. It defines what speed means in our universe. It's woven into the very fabric of space and time, like a fundamental constant that holds reality together. Think of it this way. When you walk across a room, you're not just moving through empty space, you're moving through space-time itself, a four-dimensional tapestry where space and time are interwoven. Light speed is the rate at which this tapestry allows information to travel from one point to another. It's not that light is particularly special, it's that this speed represents the maximum rate at which cause and effect can propagate through the universe. Picture space-time as a vast ocean. Waves can travel across this ocean, but only at a certain maximum speed. Light waves, radio waves, gravitational waves. They all surf this cosmic ocean at exactly the same speed. It's not that they're trying to go this fast. It's that this is the only speed the ocean of space-time allows. Now, here's where it gets beautifully strange. This speed limit isn't just a suggestion. It's enforced by the universe itself through the laws of physics. As you approach light speed, something remarkable happens. Your mass effectively increases. Time slows down for you relative to the outside world. The energy required to accelerate you further approaches infinity. It's as if the universe is saying, I see what you're trying to do, and I'm going to make it progressively more difficult until it becomes impossible. The closer you get to light speed, the more the universe resists your efforts. It's like trying to push through increasingly thick cosmic molasses. It's as if the universe is saying, I see what you're trying to do, and I'm going to make it progressively more difficult until it becomes impossible. The closer you get to light speed, the more the universe resists your efforts. But why this particular speed? Why not twice as fast or half as fast? The answer lies in the fundamental structure of reality itself. This speed limit emerges from the geometry of space-time, from the way space and time are related to each other. It's not arbitrary. It's a consequence of the deepest mathematical relationships that govern existence. Consider that every interaction in the universe respects this limit. When you flip a light switch, the electrical signal travels at light speed. When you look at a star, you're seeing it as it was when its light began its journey to you. When particles collide in accelerators, they follow the relativistic rules that this speed limit imposes. This cosmic speed limit also means that the universe has a fundamental grain of simultaneity. Events that seem simultaneous to you might not be simultaneous to someone moving very fast relative to you. The speed of light creates a bubble of now around each observer, and these bubbles can stretch and compress depending on motion. In essence, Light speed isn't just about light. It's about the maximum rate at which reality can update itself. It's the cosmic refresh rate, the fundamental clock speed of the universe. And tonight, we're going to imagine what happens when we somehow manage to exceed this ultimate boundary. Let me tell you a story about two scientists who accidentally discovered something that would change our understanding of reality forever. Their names were Albert Michelson and Edward Morley, and in 1887, they were trying to measure something that didn't exist. At the time, scientists believed that light waves needed something to travel through, just like sound waves need air. They called this mysterious substance the luminiferous ether, an invisible medium that filled all of space. The idea was that Earth must be moving through this ether as it orbits the sun, creating an ether wind that would affect the speed of light in different directions. Picture yourself riding in a boat across a flowing river. If you shine a flashlight upstream, the light should travel slower relative to the shore because it's fighting the river's current. Shine it downstream, and it should travel faster. This is what Michelson and Morley expected to find with light traveling through the ether. They built an incredibly precise instrument called an interferometer. It split a beam of light into two perpendicular paths, then brought them back together. If Earth was moving through the ether, the light traveling in the direction of Earth's motion should take a different amount of time than the light traveling perpendicular to it. When the beams recombined, they should create an interference pattern that would reveal the ether wind. But something strange happened. No matter how they oriented their equipment, no matter what time of day or year they conducted the experiment, the speed of light remained exactly the same in all directions. The ether wind simply wasn't there. This was deeply puzzling. It was like discovering that when you throw a ball forward from a moving train, it doesn't go faster than if you threw it from a stationary platform. Common sense says that speed should add together, but light was behaving as if it didn't care about the motion of its source or the observer. Other scientists tried to explain this result. Maybe the ether was somehow dragged along with Earth. Maybe the apparatus was contracting in the direction of motion. These explanations became increasingly elaborate and unsatisfying. Then, in 1905, a young patent clerk named Albert Einstein proposed something radical. What if there was no ether at all? What if light always travels at the same speed, regardless of the motion of the source or observer? What if this constant speed was a fundamental property of the universe itself? This insight led to special relativity, one of the most profound revolutions in human thought. Einstein realized that if light speed is constant, then our intuitive notions of space and time must be wrong. Time isn't absolute. It can slow down or speed up, depending on motion. Space isn't fixed. It can contract and expand. The implications were staggering. Imagine you're traveling in a spaceship at 90% of light speed. You turn on a flashlight. From your perspective, the light leaves the flashlight at light speed. But from the perspective of someone watching you zoom by, that light is also traveling at light speed, not light speed plus your ship's speed. The universe adjusts space and time themselves to keep light speed constant. This constancy of light speed means that the universe has a built-in translation system. When observers moving at different speeds measure the same event, they might disagree about when it happened or how much space it occupied, but they'll always agree that light travels at the same speed. It's as if the universe has a fundamental speed limit that's so important, it's willing to bend space and time to enforce it. This speed isn't just the speed of light, it's the speed of causality itself, the maximum rate at which cause and effect can propagate through reality. The Michelson-Morley experiment, intended to detect the ether, instead revealed something far more profound, that the universe operates according to principles that defy our everyday experience. It showed us that space and time aren't the fixed stage on which physics plays out. They're dynamic participants in the cosmic dance. And this discovery set the stage for our journey tonight. Because if light speed is truly constant and truly fundamental, then imagining what happens when we exceed it takes us into territory where the normal rules of physics break down in the most fascinating ways. Let me guide you through one of the most elegant and unforgiving barriers in all of physics. It's a barrier that seems almost alive in its determination to prevent anything from exceeding light speed. The universe has built-in mechanisms that become increasingly dramatic as you approach this cosmic speed limit. First, let's talk about what happens to mass. Well, this is where things get beautifully strange. As you accelerate faster and faster, your mass doesn't just stay the same. It increases, not because you're gaining more atoms, but because mass and energy are two faces of the same coin, and kinetic energy contributes to mass. Picture yourself in a spaceship, accelerating steadily. At first, everything feels normal, but as you approach significant fractions of light speed, something remarkable happens. Your mass begins to grow. At 90% of light speed, your mass has more than doubled. At 99%, it's increased by a factor of 7. At 99.9%, it's grown by a factor of 22. Now imagine trying to accelerate further. You need more and more energy to budge your increasingly massive spaceship. It's like trying to push a boulder that keeps getting heavier with every step. The universe is literally making you more massive to prevent you from going faster. But it gets even more dramatic. As you approach light speed, your mass approaches infinity, and to accelerate infinite mass requires infinite energy. Since infinite energy doesn't exist in our universe, you can never quite reach light speed, let alone exceed it. Intuit, fall, intuit, selfie, when at more to strength. It's an asymptotic barrier. You can get arbitrarily close, but you can never actually reach it. This isn't just about spaceships. It applies to every particle with mass. Protons in particle accelerators experience this same effect as we pump more energy into them. They don't just get faster indefinitely, they get more massive. The energy goes into increasing their mass rather than their speed beyond a certain point. Now let's consider time dilation, another guardian of the light speed barrier. As you approach light speed, time itself begins to slow down for you relative to the outside world. At 90% of light speed, time passes about half as fast for you. At 99%, it's slowed to about 1/7. At 99.9%, it's crawling at 1/22nd, the normal rate. Imagine watching the universe from this perspective. Stars would appear to race through their life cycles. Civilizations would rise and fall in what seems like moments to you. The universe would age around you while you experience time at a glacial pace. But here's the crucial point. From your perspective, you never actually reach light speed. The universe always appears to be updating normally around you. It's only when you compare your experience to someone in a different reference frame that the time dilation becomes apparent. There's also length contraction to consider. As you approach light speed, the universe in your direction of travel appears to contract. Distances shrink. The galaxy itself would appear to flatten in front of you, compressed into an increasingly thin pancake. At light speed, this contraction would be complete. The universe would have zero thickness in your direction of travel. But perhaps the most fundamental barrier is energy. The energy required to accelerate an object follows a specific mathematical relationship. As your speed approaches light speed, the energy required approaches infinity. This isn't just a practical problem. It's a fundamental limitation built into the geometry of space-time itself. Think of it this way. The universe has a maximum energy density. Beyond this point, space and time themselves break down. The energy required to reach light speed would exceed this maximum, creating conditions where the normal laws of physics simply don't apply. Einstein's equations show us that mass, energy, space, and time are all interconnected. They form a self-consistent system where attempting to violate one law automatically triggers responses in the others. It's as if the universe has multiple backup systems to prevent faster-than-light travel. Even massless particles like photons can only travel at light speed, never faster, never slower. They exist in a special state where they experience no time and no distance. From a photon's perspective, it's created and absorbed in the same instant, regardless of how far it travels from our perspective. The beautiful irony is that the universe's prohibition against faster-than-light travel isn't cruel, it's protective. It preserves causality, prevents paradoxes, and maintains the logical structure of reality. Without this speed limit, cause and effect could become scrambled, creating logical contradictions that would make a coherent universe impossible. So the question becomes, what would happen if we could somehow overcome these barriers? What if we could bypass the universe's built-in protection systems and venture into the realm beyond light speed? That's the impossible journey we're about to take together. Imagine standing at the edge of the ultimate cliff in physics. Below you lies the familiar world where nothing moves faster than light, where cause precedes effect, where time flows in one direction. Above you stretches the unknown realm of faster-than-light travel, where the fundamental rules of reality begin to unravel. What would the moment of transition feel like? Picture yourself in a spacecraft that has somehow overcome the infinite energy barrier. You're approaching light speed, and the universe around you is behaving strangely. Time is slowing to a crawl. The stars ahead have blue shifted into a brilliant ring of light, while the stars behind have red-shifted into invisibility. Your mass has grown enormous, and space-time itself is warping around you. Then, somehow, you cross the threshold. The first thing you might notice is that the concept of now becomes meaningless. In the normal world, there's a clear distinction between past, present, and future. But in the faster-than-light realm, these concepts become fluid. You might observe events happening in reverse order from your perspective, with effects preceding their causes. Your relationship with the rest of the universe would become fundamentally broken. In the normal world, you can always send a signal to another part of the universe and know that it will arrive after you send it. But traveling faster than light means you could potentially arrive somewhere before a light signal you sent from your starting point. You would become causally disconnected from the universe you left behind. The very structure of space-time would respond to your presence in ways that are difficult to imagine. In Einstein's relativity, faster-than-light travel is associated with imaginary numbers in the mathematical equations. This isn't just a mathematical curiosity. It suggests that faster-than-light travel might exist in a realm where the normal rules of physics are turned inside out. Consider what happens to the concept of simultaneity. In the normal world, events that are simultaneous in one reference frame might not be simultaneous in another, but there's still a consistent logical structure. In the faster-than-light realm, this structure breaks down completely. Events could be simultaneous, sequential, or even occur in reverse order depending on your perspective. Your interaction with light itself would become paradoxical. Light traveling in the same direction as you would appear to be moving backwards. Light traveling towards you would appear to be moving at incredible speeds. Sirian appear to be moving at incredible speeds. Your interaction with light itself would become paradoxical. Light traveling in the same direction as you would appear to be moving backwards. Light traveling towards you would appear to be moving backwards. Light traveling towards you would appear to be moving at incredible speeds. The familiar constant of light speed would become variable and direction-dependent from your perspective. The electromagnetic fields that permeate space would behave strangely around you. These fields carry information about the state of the universe, but in the faster-than-light realm, you would be outrunning this information. You might find yourself in regions of space where the electromagnetic fields haven't yet learned about events that have already occurred elsewhere. Temperature and entropy would become problematic concepts. In the normal world, temperature is related to the average kinetic energy of particles, and entropy always increases. But in the faster-than-light realm, these concepts might reverse or become undefined. You could encounter regions where entropy decreases, where heat flows from cold to hot, where the second law of thermodynamics runs backward. The vacuum itself would respond to your presence. In quantum field theory, the vacuum isn't empty. It's filled with virtual particles that pop in and out of existence. These virtual particles respect the speed of light limit, but your faster-than-light travel would create discontinuities in the vacuum state, potentially causing it to decay into new configurations. Perhaps most disturbing would be the effect on causality itself. In the normal world, you can trace a clear chain of cause and effect for any event, but in the faster-than-light realm, this chain becomes tangled and potentially circular. You might find yourself in situations where you've caused events that led to your own departure, creating closed causal loops. The concept of distance would become ambiguous. In the normal world, there's a clear relationship between space and time through the speed of light. But in the faster-than-light realm, this relationship breaks down. Space and time might become decoupled, or they might couple in new and unexpected ways. Your very existence in this realm would be paradoxical. The equations that describe faster-than-light particles, called tachyons, suggest that they would have imaginary mass and would slow down when energy is added to them. This is the opposite of normal matter, which has real mass and speeds up when energy is added. The boundary between the faster-than-light realm and the normal world would be impermeable in both directions. Once you cross into the faster-than-light realm, you might find it impossible to return to the normal world, just as normal matter finds it impossible to reach light speed. This transition would represent more than just a change in speed. It would be a fundamental phase transition in the nature of reality itself, like the difference between matter and antimatter, or between real and imaginary numbers. You would be crossing into a mirror universe where the fundamental laws of physics operate in reverse. Let's delve into perhaps the most fundamental obstacle to faster-than-light travel, the energy problem. It's not just that you need a lot of energy, it's that you need an impossible amount of energy. And the universe seems designed to prevent you from obtaining it. In our normal world, energy has a clear relationship with motion. The faster you want to go, the more energy you need. For everyday speeds, this relationship is straightforward. Double your speed, and you need 4 times the energy. It's manageable, predictable, and intuitive. But as you approach significant fractions of light speed, something remarkable happens. The energy required doesn't just increase, it increases dramatically. At 90% of light speed, you need about twice as much energy as classical physics would predict. At 99%, you need about 7 times as much. At 99.9%, you need 22 times as much. This isn't just an engineering challenge, it's a fundamental barrier built into the structure of space-time itself. The energy required to accelerate an object approaches infinity as its speed approaches light speed. Infinite energy doesn't exist in our universe, so light speed becomes an asymptotic barrier that can never be reached. But let's imagine for a moment that we could somehow overcome this barrier. What would happen to the energy budget of the universe? If you could access infinite energy to reach light speed, and then somehow access even more energy to exceed it, you would be tapping into something beyond the normal energy economy of the cosmos. This brings us to the strange world of tachyons, hypothetical particles that always travel faster than light. The mathematics that describe tachyons are fascinatingly bizarre. Unlike normal particles, tachyons would have what physicists call imaginary mass. This doesn't mean they're not real. It means their mass is described by imaginary numbers, mathematical entities that involve the square root of -1. The energy behavior of tachyons would be completely opposite to normal matter. When you add energy to a normal particle, it speeds up, but when you add energy to a tachyon, it slows down. To make a tachyon go faster, you would need to remove energy from it. At infinite speed, a tachyon would have 0 energy. This is the mirror image of normal matter, which has infinite energy at light speed. This creates a strange energy landscape. Normal matter lives in a valley where light speed represents an infinitely high energy barrier. Tachyons would live in a separate valley on the other side of this barrier, where light speed represents an infinitely low energy barrier. Neither type of matter can cross into the other's domain. The universe's energy budget would become paradoxical in the presence of faster-than-light travel.
If you could somehow create tachyons from normal matter, you would be violating conservation of energy in a fundamental way.
The total energy of the universe would become undefined or infinite. Consider what happens to kinetic energy in the faster-than-light realm. Kinetic energy is typically positive and increases with speed, but for tachyons, kinetic energy would decrease with speed and could become negative. This would mean that a faster-than-light particle moving at infinite speed would have negative infinite energy, whatever that might mean. The concept of rest mass also becomes problematic. Normal particles have a well-defined rest mass. Their mass when not moving, but tachyons can never be at rest. They're always moving faster than light. So the concept of rest mass becomes meaningless. Instead, they would have a minimum energy at infinite speed. This energy paradox extends to thermodynamics. In the normal world, heat flows from hot to cold, and entropy always increases. But in the faster-than-light realm, these relationships might reverse. You could have systems where heat flows from cold to hot, where entropy decreases, where the second law of thermodynamics runs backward. The vacuum itself would have a different energy state in the presence of faster-than-light travel. The quantum vacuum is filled with virtual particles that pop in and out of existence. And these virtual particles respect the speed of light limit. But faster-than-light travel would create discontinuities in the vacuum, potentially causing it to decay into new energy states. The sekbis in the QD, perhaps most disturbing, is the possibility of negative energy. Some solutions to Einstein's equations that allow faster-than-light travel require the existence of negative energy or negative mass. This exotic matter would have gravitational effects opposite to normal matter. It would repel rather than attract. The energy problem isn't just about having enough fuel for your faster-than-light spacecraft. It's about the fundamental consistency of the universe's energy budget. The universe appears to be designed in such a way that faster-than-light travel would require violating the most basic conservation laws. This suggests that the energy barrier to faster-than-light travel isn't just a practical obstacle. It's a fundamental feature of reality that maintains the logical consistency of the universe. Without this barrier, the concepts of energy, mass, and momentum would become ill-defined, and the universe would lose its mathematical coherence. Yet tonight, we're imagining what lies beyond this barrier, in the realm where energy behaves in ways that challenge our most fundamental assumptions about the nature of reality. Now let's explore what might happen to time itself in the realm beyond light speed. Time, that most fundamental dimension of our experience, would behave in ways that challenge not just our understanding of physics, but our very perception of reality. In our normal world, time has a clear direction. It flows from past to future, and this flow is intimately connected to the speed of light. Information about events propagates at light speed, creating a causal structure where causes precede effects. But in the faster-than-light realm, this structure would crumble. Imagine looking at your watch as you travel faster than light. The concept of now becomes meaningless when you're outrunning the very signals that define simultaneity. You might observe events happening in reverse chronological order. A star might appear to gather its light back into itself, unburn its fuel, and collapse into the nebula from which it formed. This isn't just a visual illusion, it's a fundamental breakdown of temporal causality. When you travel faster than light, you're moving through space-time in a way that violates the normal relationship between space and time. You're creating a situation where temporal order becomes observer-dependent in an extreme way. Consider what happens to the concept of memory. Memory relies on the fact that past events influence present brain states. But in the faster-than-light realm, the relationship between past and present becomes scrambled. You might find yourself remembering events that haven't happened yet, or forgetting events that are happening now. The mathematics of special relativity provide clues about time's behavior in this forbidden realm. The equations that describe time dilation contain square roots, and when you plug in faster than light speeds, these square roots become imaginary numbers. The square roots become imaginary numbers. The more hantain bente, the mindjav of shefiturari. This suggests that time itself might become imaginary in some sense. The square roots, 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 the square. What could imaginary time mean? It might represent a dimension perpendicular to normal time, a sideways movement through temporal space. Instead of moving forward or backward through time, you might be moving in a direction that has no equivalent in our normal experience. The concept of aging would become paradoxical. In the normal world, aging is driven by entropy, the natural tendency of systems to become more disordered over time. But in the faster-than-light realm, entropy might flow backward, causing aging to reverse. You could become younger as you travel, returning to earlier states of biological organization. Your relationship with causality would be fundamentally altered. In the normal world, you can influence the future, but not the past. But faster-than-light travel would allow you to influence events in your own past. But faster-than-light travel would allow you to influence events in your own past. But when we are certain, this certain theory, you could potentially prevent your own departure, creating logical paradoxes that have no resolution. The psychological effects would be profound. Human consciousness depends on the orderly flow of time. Our sense of identity is built on the continuity of memory from past to present. In the faster-than-light realm, this continuity would be disrupted. You might experience consciousness as a fragmented, non-linear phenomenon. Time dilation would behave in reverse. In the normal world, time slows down for you as you approach light speed, but in the faster-than-light realm, time might speed up in unusual ways. You could experience entire eons in moments, or find moments stretching into eternities. The concept of simultaneity would become completely relative. Events that appear simultaneous from one faster-than-light perspective might appear to occur in different orders from another perspective. The universe would lose its shared timeline, becoming a collection of incompatible temporal experiences. Quantum mechanics would interact with time in strange ways. Quantum events rely on probabilistic time evolution, but in the faster-than-light realm, quantum states might spontaneously collapse into earlier configurations or evolve in ways that violate our understanding of quantum mechanics. The thermodynamic arrow of time would be disrupted. In the normal world, time's direction is defined by increasing entropy, but in the faster-than-light realm, entropy might decrease, causing time to flow backward from a thermodynamic perspective. Hot objects might spontaneously become cold, and ordered systems might spontaneously become more organized. Perhaps most disturbing would be the possibility of closed time-like curves. These are paths through space-time that loop back on themselves, allowing travel into the past. Faster-than-light travel could create such curves, enabling paradoxes where effects precede causes and where the future influences the past. Which the future influences the past. Which the future influences the past. C. The universe's timeline would become fractured. Instead of a single coherent history, there might be multiple incompatible timelines. Events could occur in different orders depending on your perspective, and the concept of a universal now would disappear. Winchwitz, if you disabnd into FOD. Each universe's timeline would become fractured. Communication with the normal world would become temporally impossible. Any signal you sent back to the slower-than-light universe might arrive before you sent it, creating causal loops and paradoxes. The faster-than-light realm would be temporally isolated from the normal world. Time itself might become quantized or discrete rather than continuous. The smooth flow of time we experience might break down into discrete jumps or steps. Reality might update itself in chunks rather than flowing smoothly. This temporal chaos suggests that the universe's prohibition against faster-than-light travel isn't just about energy or causality. It's about preserving the coherent flow of time that makes reality possible. Without this prohibition, time would become a jumbled, paradoxical dimension where the very concept of existence becomes questionable. Close your eyes and imagine yourself approaching the speed of light. The journey begins gently, almost imperceptibly. At first, as your spacecraft accelerates, Everything feels normal. The stars ahead look like stars. The stars behind look like stars. And time flows at its familiar pace. But as you reach about 10% of light speed, something subtle begins to change. The stars directly ahead start to appear slightly bluer than they should, while the stars behind take on a faint reddish tint. This is the Doppler effect in action. Light waves are being compressed in front of you and stretched behind you. It's like the universe is starting to hint at the strangeness to come. At 50% of light speed, the transformation becomes more dramatic. The stars ahead have shifted from blue to ultraviolet, though your eyes can no longer see them directly. The stars behind have faded to deep red, then infrared, then radio waves. The familiar constellations begin to distort as the entire sky reshapes itself around your motion. Now imagine reaching 90% of light speed. The universe has become an alien place. Nearly all the stars have vanished from view, compressed into a brilliant ring of light directly ahead of you. This ring blazes with the collected light of the entire visible universe, concentrated into a narrow cone. Behind you, the universe has faded to near darkness, its light red shifted beyond perception. Time itself has become your companion in strangeness. Your watch ticks normally from your perspective, but if you could somehow observe the universe you left behind, you would see it moving in slow motion. Planets crawl through their orbits, stars pulse with leisurely rhythm, and the dance of galaxies becomes a nearly frozen tableau. At 99% of light speed, you're living in a universe of extremes. The ring of light ahead has become blindingly intense, a concentrated beam of every photon in the universe rushing toward you. Your mass has grown sevenfold, though you feel no different. Space itself has contracted. Distances in your direction of travel have shortened dramatically, making the universe appear flattened like a cosmic pancake. But now comes the impossible moment. Somehow, through means that defy physics, you continue to accelerate. You approach light speed asymptotically, and then, impossibly, you cross the threshold. The transition is unlike anything in human experience. It's not just a change in speed, it's a phase transition in the nature of reality itself. The normal relationship between space and time breaks down. The familiar concepts of before and after, here and there, cause and effect, begin to lose their meaning. In the faster-than-light realm, the universe reveals itself as a place where the normal rules are turned inside out. The brilliant ring of light that was ahead of you at near-light speed begins to behave strangely. Light that was racing toward you now appears to be moving backward, as if the universe is rewinding itself around your motion. Your perception of distance becomes paradoxical. In the normal world, distance is absolute. A light year is a light year, regardless of your motion. But in the faster-than-light realm, distance becomes relative in extreme ways. The space between objects might appear to expand or contract, depending on your speed and direction. The concept of simultaneity crumbles completely. Events that were clearly sequential in the normal world might appear to occur in reverse order. You might observe a star exploding before it finishes forming, or see civilizations decline before they rise. The universe's timeline becomes scrambled from your perspective. Temperature and heat behave strangely in this realm. In the normal world, heat always flows from hot to cold, and entropy always increases. But in the faster-than-light realm, these relationships might reverse. You could encounter regions where heat flows uphill, where entropy decreases, where the second law of thermodynamics runs backward. The electromagnetic fields that permeate space would create bizarre effects around you. These fields carry information about the state of the universe, but you're now outrunning this information. You might find yourself in regions where the fields haven't yet learned about events that have already occurred elsewhere. Your relationship with the quantum vacuum would become exotic. The vacuum isn't empty. It's filled with virtual particles that pop in and out of existence. But these virtual particles respect the speed of light limit. Your faster-than-light travel would create discontinuities in the vacuum, potentially causing it to decay into new configurations. Perhaps most disconcerting would be the breakdown of causality itself. In the normal world, you can trace a clear chain of cause and effect for any event. But in the faster-than-light realm, this chain becomes tangled. You might find yourself in situations where you've caused events that led to your own departure, creating closed causal loops. The boundary between the faster-than-light realm and the normal world would be impermeable. Just as normal matter cannot reach light speed, faster-than-light matter cannot slow down to light speed. You would be trapped in this exotic realm, unable to return to the normal universe. This relativistic landscape would be more than just a strange place to visit. It would be a fundamental alteration of reality itself. The universe you thought you knew would be revealed as just one phase of a larger, more complex reality, where the normal rules are merely special cases of deeper, more exotic laws. Now that you've crossed the impossible threshold, let's explore what the universe looks like from your faster-than-light perspective. You've entered a realm where the very concept of looking takes on new meaning, where light itself behaves in ways that challenge the foundations of perception. From your position in the faster-than-light realm, light appears to be moving backward. This isn't just a visual illusion. It's a fundamental consequence of your exotic motion. The light that was traveling toward you at light speed now appears to be racing away from you at whatever speed you're traveling, minus the speed of light. If you're moving at twice light speed, light appears to be moving backward at light speed. This creates a universe where the normal relationship between seeing and knowing is completely inverted. When you look at a star, you're not seeing it as it was when its light left. You're seeing it as it will be when your faster-than-light influence reaches it. The universe becomes a window into its own future rather than its past. The cosmic microwave background radiation, the afterglow of the Big Bang that normally bathes the universe in gentle warmth, would appear completely different. Instead of being a nearly uniform glow coming from all directions, it would appear as a bright beacon pointing in the direction of your motion. The entire early history of the universe would be compressed into a narrow cone of intense radiation. Galaxies would appear to be moving in reverse, their spiral arms unwinding, their stars gathering back into the primordial gas clouds from which they formed. The entire process of cosmic evolution would appear to be running backward, with complex structures dissolving into simpler ones, with order decreasing and chaos increasing. But here's where it gets truly strange. From your perspective, you would still experience a coherent causal universe. Events would still follow logical sequences from your point of view. It's only when you compare your experience to the normal universe that the contradictions become apparent. The night sky would be divided into distinct regions. Ahead of you, in the direction of your motion, would be a region of intense brightness, where all the universe's light is concentrated and blue shifted to extreme energies. Behind you would be a region of relative darkness, where light has been redshifted beyond visibility. But unlike the normal universe, where light carries information about the past, the light you observe would carry information about the future. You would be seeing events before they happen in the normal universe's timeline. This prophetic vision would come at a cost. You would be causally disconnected from the events you observe. The concept of distance would become fluid. In the normal universe, the distance to a star is determined by how long its light takes to reach you. But in the faster-than-light realm, this relationship breaks down. You might observe objects that are causally in your future, making the concept of distance ambiguous. Quantum mechanics would present a strange spectacle. Quantum events, which normally evolve forward in time through probability waves, would appear to evolve backward. You might observe quantum states spontaneously collapsing into earlier configurations or evolving in ways that violate the normal understanding of quantum mechanics. The expansion of the universe would appear to be reversed. Instead of galaxies moving away from each other, they would appear to be converging, racing toward a future big crunch. The universe's timeline would seem to be running backward, with complexity decreasing and entropy flowing in reverse.
It's just toe.
Your view of black holes would be particularly fascinating. These objects, which normally appear as dark voids that swallow light, would appear as bright beacons radiating energy. You would be seeing the time-reversed view of black holes, where they appear to be creating matter and energy rather than consuming it. The boundary between the faster-than-light realm and the normal universe would be visible as a kind of cosmic event horizon. This boundary would separate the regions where causality runs forward from regions where it runs backward. You would be able to observe this boundary, but you would be unable to cross it. Perhaps most disconcerting would be your view of intelligent life. Civilizations would appear to be evolving backward, with advanced technologies dissolving into simpler forms, with knowledge being forgotten rather than discovered. You would witness the tragic spectacle of consciousness undoing itself, of intelligence flowing backward into ignorance. The cosmic web, the large-scale structure of the universe, would appear to be dissolving. Galaxy clusters would fragment into individual galaxies, which would then fragment into individual stars, which would then fragment into gas clouds. The entire hierarchy of cosmic structure would appear to be collapsing. Your instruments would register impossible readings. Thermometers would show heat flowing from cold to hot. Clocks would run backward. Entropy meters would show disorder decreasing. Every measurement would contradict the normal understanding of physical law. But perhaps the most profound aspect of your view would be the realization that you're observing a universe where the arrow of time has been reversed. From your perspective, the future is determining the past, effects are preceding causes, and the logical structure of reality has been turned inside out. This view from beyond would be more than just a different perspective on the same universe. It would be a glimpse into a fundamentally different reality, where the normal rules of existence are reversed, where the future flows into the past, and where the very concept of causality takes on new meaning. Imagine trying to send a message home from the faster-than-light realm. This simple act, which seems so natural in our everyday world, becomes one of the most profound impossibilities in physics. The very concept of communication breaks down when you're traveling faster than the information you're trying to send. Let's start with the basics of communication. In the normal world, communication works because information travels at light speed. When you speak, sound waves carry your words through the air. When you send a radio signal, electromagnetic waves carry your message through space. All of these signals respect the cosmic speed limit. But now you're traveling faster than light itself. Any signal you try to send back to the normal universe would be racing against your own motion. If you're traveling at twice light speed and you send a light signal backward, that signal would appear to be moving at light speed from your perspective, but it would be moving at light speed minus your speed, which is negative light speed, from the perspective of the normal universe. This creates a paradox of arrival. Your signal would arrive before you sent it, violating the normal relationship between cause and effect. The recipients of your message would receive it before you transmitted it, creating a causal loop that defies logical explanation. Consider trying to send a simple message. Hello, I have successfully exceeded light speed. From your perspective, you compose this message and transmit it. But from the perspective of the normal universe, the message arrives before you left, before you even decided to attempt faster than light travel. The effect precedes the cause. This isn't just a technical problem. It's a fundamental breakdown of the concept of information itself. Information, in the physics sense, is the ability to distinguish between different possible states. But in the faster-than-light realm, this distinction becomes meaningless when the information arrives before the states it describes have been determined. The quantum mechanics of communication would become bizarre. In the normal world, quantum information follows strict rules about entanglement and measurement, but faster-than-light communication would violate these rules, potentially allowing for the instantaneous transmission of information across any distance. This would break the fundamental symmetries that underlie quantum mechanics. Even more disturbing would be the possibility of communication with your own past. If you could send signals that travel faster than light, you could potentially send a message to yourself before you left, warning yourself not to make the journey. This creates a grandfather paradox in space. You could prevent your own departure, but then you wouldn't be in the faster-than-light realm to send the message. The concept of language itself would become problematic. Language depends on shared reference frames and common understandings of time and causality. But in the faster-than-light realm, these shared foundations would be absent. Your words might arrive before their meanings have been determined, creating semantic paradoxes. Think about the psychological implications. Communication is fundamental to human consciousness and identity. We define ourselves through our interactions with others, through our ability to share thoughts and experiences. But in the faster-than-light realm, this sharing would be impossible. You would be isolated, not just physically, but informationally. The electromagnetic spectrum would behave strangely around your communication attempts. Radio waves, which normally travel at light speed, would appear to be moving backward from your perspective. Any attempt to modulate these waves with information would create signals that arrive before they're sent, scrambling the temporal order of the information. Digital communication would face even more severe problems. Digital signals rely on precise timing and synchronization, but in the faster-than-light realm, timing becomes meaningless. Your digital messages would arrive as scrambled nonsense, their temporal structure destroyed by the violation of causality. The concept of acknowledgement would become impossible. In normal communication, you send a message and wait for a response. But in the faster-than-light realm, responses would arrive before messages are sent. The normal back and forth of conversation would collapse into a jumbled sequence of cause and effect. Perhaps most troubling would be the realization that your faster-than-light journey would be inherently solitary. You would be unable to share your experiences with anyone in the normal universe. Your discoveries, your observations, your very existence in the faster-than-light realm would be incommunicable. This communicational isolation would extend to your own memory and consciousness. Memory depends on the ability to encode and retrieve information across time. But in the faster-than-light realm, where time behaves strangely, even your own thoughts might become scrambled. You might find yourself remembering events that haven't happened yet, or forgetting events that are happening now. The universe's prohibition against faster-than-light travel isn't just about energy or causality. It's about preserving the possibility of communication itself. Without this prohibition, the concept of information would break down, making coherent reality impossible. This communication barrier suggests that the faster-than-light realm, if it exists, would be fundamentally lonely. It would be a place where consciousness exists in isolation, where experiences cannot be shared, where the very notion of interacting with others becomes meaningless. Your journey into the faster-than-light realm would be more than just a physical journey. It would be a journey into absolute solitude, where the basic human need for communication and connection becomes impossible to fulfill. Welcome to the most mind-bending aspect of faster-than-light travel, the complete breakdown of causality itself. In our normal world, causes precede effects with the reliability of sunrise. You flip a switch, then the light turns on. You speak, then someone hears you. You send a letter, then it arrives. This sequence is so fundamental to our understanding of reality that we rarely question it. But in the faster-than-light realm, this sacred order crumbles. Effects can precede their causes, creating logical paradoxes that challenge the very foundations of rational thought. Let me guide you through this conceptual maze with the gentleness it deserves. Imagine you're in your faster-than-light spacecraft, traveling at twice the speed of light. You decide to send a signal back to Earth, announcing your successful journey. From your perspective, you compose the message and transmit it. But here's where reality becomes strange. Your signal would arrive on Earth before you sent it. This isn't just a timing error, it's a fundamental violation of causality. The effect, Earth receiving your message, occurs before the cause. You sending the message, from Earth's perspective, your message arrives from the future, carrying information about events that haven't happened yet. Now let's make this even more paradoxical. Suppose Earth receives your message and responds immediately, telling you not to send the original message. Their response, traveling at light speed, would reach you before you sent your original message. You would receive an instruction not to do something you haven't done yet. This creates what physicists call a causal loop. The response causes you not to send the original message, but the response only exists because of the original message. It's like a cosmic chicken and egg problem, where neither the chicken nor the egg can exist without the other. Consider a more dramatic example. Imagine you observe a star exploding in the faster-than-light realm. From your perspective, This explosion happens at a specific moment, but because you're traveling faster than light, you could potentially send a signal warning the star's planets about the explosion before it occurs from their perspective. This creates a situation where the effect, the warning, precedes the cause, the explosion. The civilizations on those planets would receive warning of their star's death before their star actually explodes. They could potentially evacuate, changing the entire outcome of the event. But here's where it gets truly paradoxical. If the civilizations evacuate because of your warning, and if their evacuation somehow prevents or delays the explosion, then the explosion you observed might never occur. But if the explosion never occurs, then you never observed it, and you never sent the warning. The entire causal chain becomes self-contradictory. The mathematical description of these paradoxes involves what physicists call closed, time-like curves. These are paths through space-time that loop back on themselves, allowing information or objects to travel into their own past. Faster-than-light travel naturally creates such curves, enabling all manner of causal paradoxes. Think about the implications for free will. In the normal world, you make choices that influence the future, but in the faster-than-light realm, your future actions could influence your past decisions. You might find yourself making choices because of their consequences, even though those consequences haven't occurred yet. The concept of personal identity becomes problematic. Are you the same person who made the decision to travel faster than light, or are you a different person who exists in a causally disconnected realm? If your actions can influence your own past, what does it mean to be a continuous, coherent self? Information theory breaks down completely in the presence of causal loops. Information is supposed to distinguish between different possible states, but when effects precede causes, all states become simultaneously possible and impossible. The universe loses its ability to maintain coherent information about itself. Even more disturbing is the possibility of spontaneous causation. In the normal world, every effect has a cause, but in the faster-than-light realm, you could encounter effects that appear to have no cause, or causes that appear to have no effect. Events could spring into existence without explanation, or disappear without reason. The logical structure of reality would become self-referential and paradoxical. You might encounter situations where the truth of a statement depends on its own truth value, creating logical loops that have no resolution. The universe would become a place where contradictions are not just possible, but inevitable. Consider the implications for memory and knowledge. In the normal world, you remember the past and anticipate the future. But in the faster-than-light realm, you might remember events that haven't happened yet, or forget events that are happening now. Knowledge itself would become temporally scrambled. The universe's prohibition against faster-than-light travel isn't just about preserving energy conservation or preventing paradoxes. It's about preserving the logical consistency of reality itself. Without this prohibition, the universe would become a place where rational thought is impossible, where causality is meaningless, and where the very concept of existence becomes paradoxical. This suggests that the speed of light isn't just a barrier to faster travel. It's a barrier that protects the universe from logical inconsistency. It's the cosmic firewall that keeps reality coherent and comprehensible. Let's explore one of the most famous paradoxes in physics, but with a cosmic twist. You're probably familiar with the grandfather paradox from time travel stories. If you travel back in time and prevent your grandfather from meeting your grandmother, then you would never be born, but then you couldn't have traveled back in time to prevent their meeting. It's a logical loop that seems to have no resolution. Now imagine this same paradox playing out across the vast distances of space through faster-than-light travel. The principles are the same, but the scale is cosmic, and the implications are even more mind-bending. Picture yourself in your faster-than-light spacecraft, having successfully exceeded the speed of light. You're now traveling at, say, 3 times light speed toward a distant star system. This star system is 100 light-years away, and you reach it in about 33 years of your time. From your perspective, this is a straightforward journey. But here's where the paradox begins. Because you've traveled faster than light, you arrive at the star system before light from your departure has had time to reach it. In fact, you could potentially send a signal back to your starting point that would arrive before you left, carrying information about your successful journey. Now, suppose this signal reaches your starting point and convinces the authorities there to shut down the faster-than-light program. They decide it's too dangerous and prevent your departure. But if you never departed, how did the signal arrive? And if the signal never arrived, why did they shut down the program? This is the grandfather paradox in a spatial context. Your arrival at the distant star system is both the cause and the effect of your departure. The loop is closed, and logic breaks down. Let's make this even more concrete. Imagine that your faster-than-light journey takes you to a star system where you discover a terrible cosmic disaster, perhaps a gamma-ray burst that will sterilize all life in a 1,000 light-year radius. From your advanced position, you can see this disaster approaching Earth, though it won't arrive for centuries. You decide to send a warning signal back to Earth, transmitted at light speed. Because of your faster-than-light journey, this signal arrives on Earth before the disaster is visible from Earth's perspective. Humanity receives your warning and takes steps to protect itself, perhaps by developing shields or by relocating to safer regions of the galaxy. But here's the paradox. If humanity successfully protects itself from the disaster, then the disaster doesn't occur as you observed it. The timeline has been changed. But if the disaster doesn't occur, then you never observed it, and you never sent the warning. The entire causal chain becomes self-contradictory. This creates what physicists call a closed causal loop. The warning causes the prevention, which causes the absence of the disaster, which causes the absence of the warning. It's a logical circle that has no beginning and no end. The mathematics of special relativity actually predicts these paradoxes. When you work out the equations for faster-than-light travel, you inevitably encounter situations where information can flow backward in time. This isn't a bug in the equations. It's a feature that reveals the deep connection between space and time. Consider the implications for scientific knowledge. In the normal world, we learn about the universe by observing it and making predictions. But in the faster-than-light realm, your observations could change the very events you're observing. The act of gaining knowledge about the universe would alter the universe itself. The concept of objective reality becomes problematic. In the normal world, there's a shared reality that all observers can agree on, even if they see it from different perspectives. But in the faster-than-light realm, different observers might have incompatible realities. Your reality includes events that are prevented by your very observation of them. Think about the implications for consciousness and identity. Are you the same person who made the original decision to travel faster than light? Or are you a different person existing in a causally disconnected timeline? If your actions can prevent your own past, what does it mean to have a coherent sense of self? The universe seems to have built-in protection against these paradoxes. The energy requirements for faster-than-light travel approach infinity precisely at the point where these causal loops would become possible. It's as if the universe is saying, I cannot allow this level of logical inconsistency. Some physicists have proposed that the universe has a chronology protection conjecture, a fundamental principle that prevents the formation of closed time-like curves. The idea is that quantum effects or other physical processes would intervene to prevent paradoxes from occurring. But perhaps the most elegant solution is the simplest one. Faster-than-light travel is impossible, precisely because it would lead to these unresolvable paradoxes. The universe's prohibition against exceeding light speed isn't just about energy conservation, it's about preserving logical consistency. This suggests that the speed of light is more than just a speed limit. It's a logical firewall that protects the universe from contradictions. It ensures that causes precede effects, that the past remains fixed, and that the future remains open to possibility. The grandfather paradox in space reveals that the faster-than-light realm would be more than just a strange place to visit. It would be a place where the very concept of logical consistency breaks down, where reality becomes self-contradictory, and where the universe loses its ability to maintain coherent information about itself. As we delve deeper into the impossibilities of faster-than-light travel, a remarkable pattern emerges. The universe appears to have multiple layers of protection against causality violations, as if reality itself is designed to prevent logical inconsistencies. These aren't just obstacles to overcome, they're fundamental features of existence that maintain the coherence of the cosmos. Let's begin with the most obvious defense. The energy barrier. As we've explored, accelerating any object with mass to light speed requires infinite energy. This isn't just a practical limitation, it's a mathematical impossibility. The universe simply doesn't contain infinite energy, making light speed an asymptotic barrier that can never be crossed. But imagine for a moment that you could somehow access infinite energy. The universe has a second line of defense: mass increase. As you approach light speed, your mass grows without bound. This isn't just your rest mass, it's your total relativistic mass, including all the energy you've put into acceleration. The universe is literally making you heavier to prevent you from going faster. This mass increase creates a feedback loop. The more energy you put into acceleration, the more massive you become. The more massive you become, the more energy you need to accelerate further. It's like trying to climb a mountain that grows taller with every step you take. But the universe's defenses go deeper than just energy and mass. There's also the barrier of time dilation. As you approach light speed, time slows down for you relative to the rest of the universe. At light speed, time would stop completely. This creates a temporal barrier where reaching light speed would require infinite time from the perspective of outside observers. Consider the implications. Even if you could somehow overcome the energy and mass barriers, you would still face the temporal barrier. You would need infinite time to reach light speed. And infinity is not a duration that can be achieved in any finite universe. The mathematical structure of space-time itself provides another layer of protection. Einstein's equations describe a universe where space and time are interwoven, where the geometry of space-time determines the paths that objects can follow. Faster-than-light paths simply don't exist in this geometry. They would require moving through regions of space-time that don't exist. Quantum mechanics adds its own protective mechanisms. The quantum vacuum is filled with virtual particles that pop in and out of existence. And these virtual particles respect the speed of light limit. Any attempt to exceed light speed would disrupt the quantum vacuum, potentially causing it to decay into new configurations that prevent faster-than-light travel. There's also the principle of causality itself. The universe appears to be structured in such a way that causes must precede effects. This isn't just a philosophical principle, it's built into the mathematical foundations of physics. The equations that describe particle interactions, electromagnetic fields, and gravitational waves all respect this causal structure. The concept of information provides another defense mechanism. Information theory tells us that information cannot be created or destroyed, only transformed. But faster-than-light travel would allow information to arrive before it's sent, creating situations where information appears to be created from nothing. The universe's prohibition against faster-than-light travel preserves the conservation of information. Even more subtle is the protection provided by the uncertainty principle. In quantum mechanics, you cannot simultaneously know both the position and momentum of a particle with perfect precision. This uncertainty creates a fundamental limit on how precisely you can control particle motion, making it impossible to fine-tune the conditions needed for faster-than-light travel. The thermodynamic arrow of time provides yet another layer of protection. In the normal world, entropy always increases, giving time a clear direction. But faster-than-light travel would allow for situations where entropy decreases, where heat flows from cold to hot, where the second law of thermodynamics runs backward. The universe's prohibition against faster-than-light travel preserves thermodynamic consistency. Perhaps most intriguingly, the universe appears to have a kind of cosmic immune system that responds to causality violations. Some physicists have proposed that quantum effects would automatically intervene to prevent paradoxes from occurring. Virtual particles would spontaneously appear to block faster-than-light paths, or space-time itself would develop defects that prevent causal loops from forming. This suggests that the universe has what physicists call a chronology protection conjecture, a fundamental principle that prevents the formation of closed time-like curves. The idea is that the universe actively protects itself from logical inconsistencies, using whatever physical mechanisms are necessary to maintain causal order. The anthropic principle provides another perspective on these defense mechanisms. We observe a universe with these particular laws of physics, because these are the only laws that allow for the existence of observers like us. A universe without protection against causality violations would be logically inconsistent and unable to support complex structures like stars, planets, and life. The universe's defense mechanisms aren't arbitrary restrictions. They're the conditions that make reality possible. Without the speed of light limit, the universe would be a place where logic breaks down, where causality is meaningless, and where the very concept of existence becomes paradoxical. This suggests that faster-than-light travel isn't just practically impossible, it's logically impossible. The universe's prohibition against exceeding light speed isn't a limitation to overcome, but a fundamental feature of reality that keeps the cosmos coherent and comprehensible. These defense mechanisms work together to create a universe that is both strange and stable, both mysterious and mathematically consistent. They ensure that the cosmos remains a place where rational thought is possible, where scientific discovery is meaningful, and where the future remains open to possibility. Let's venture into one of the most fascinating corners of theoretical physics, the realm of tachyons. These hypothetical particles represent a looking-glass version of our normal world, where the rules of physics are turned upside down in the most elegant and disturbing ways. The word tachyon comes from the Greek word tachys, meaning swift. These particles, if they exist, would always travel faster than light. Not sometimes, not under special conditions, but always. They would be forever trapped in the faster-than-light realm, just as normal particles are forever trapped below the speed of light. But here's where tachyons become truly strange. They would have imaginary mass. This doesn't mean they're not real. It means their mass is described by imaginary numbers, those mathematical entities that involve the square root of -1. In the equations of special relativity, imaginary mass is what emerges when you try to describe particles that travel faster than light. Picture the mass-energy relationship as a kind of mathematical landscape. Abnormal particles live in a valley where mass is positive and real. Light lives at the peak, where mass is zero. Tachyons would live in a separate valley on the other side of the peak, where mass is imaginary. Neither type of particle can cross the peak to reach the other valley. The energy behavior of tachyons would be completely inverted compared to normal matter. When you add energy to a normal particle, it speeds up. But when you add energy to a tachyon, it slows down. To make a tachyon go faster, you would need to remove energy from it. At infinite speed, a tachyon would have zero energy. This creates a bizarre energy landscape, where faster motion corresponds to lower energy. Imagine a universe where running uphill makes you go faster, where braking makes you accelerate, where the most energetic state is complete stillness. This is the world of tachyons. The relationship between energy and momentum would also be inverted. For normal particles, higher energy means higher momentum, but for tachyons, higher energy would mean lower momentum. At zero energy, a tachyon would have infinite momentum and infinite speed. Tachyones would also have a strange relationship with time. While normal particles experience time moving forward, tachyones might experience time moving backward. From a tachyone's perspective, effects might precede causes, and the universe might appear to be running in reverse. This temporal inversion would make tachyons natural time travel agents. They could carry information backward in time, creating the causal paradoxes we've explored. A tachyon emitted in the future could arrive in the past, allowing effects to precede their causes. The quantum mechanics of tachyons would be fascinatingly complex. Quantum field theory allows for tachyonic fields, fields that can propagate faster than light, but these fields are unstable and tend to decay into normal, slower-than-light particles. This instability might be the universe's way of preventing tachyons from actually existing. If tachyons could interact with normal matter, they would create exotic phenomena. They might cause normal particles to spontaneously emit energy, or they might create regions where the vacuum itself becomes unstable. The universe would become a place where energy conservation is violated in systematic ways. The detection of tachyons would be paradoxical. By the time you detect them, they would have already arrived. You might observe their effects before you observe the particles themselves. Detection experiments would need to be designed to catch particles that arrive before they're emitted. Perhaps most intriguingly, tachyons might allow for instantaneous communication across any distance. If you could modulate a tachyon beam with information, that information could travel faster than light, enabling real-time communication between distant parts of the universe. But this communication would come with a price. Causality violations, messages sent via tachyons, could arrive before they're sent, creating the grandfather paradox on a cosmic scale. The universe would become a place where information flows backward in time, where the future influences the past. The mathematics of tachyons reveals deep connections between space, time, and causality. They exist in the equations of special relativity as a kind of mathematical shadow, a reminder that the universe's prohibition against faster-than-light travel isn't absolute. It's just the boundary between two different kinds of reality. Some physicists have proposed that tachyons might actually exist as virtual particles in the quantum vacuum. These virtual tachyons would pop in and out of existence too quickly to be directly observed, but they might influence the behavior of normal particles in subtle ways. The search for tachyons has occupied physicists for decades. While no direct evidence has been found, the theoretical possibility remains tantalizing. They represent a window into a universe where the normal rules are reversed, where faster means lower energy, where time runs backward, and where causality becomes fluid. Tachyons embody the ultimate paradox of faster-than-light travel. They show us that such travel is mathematically possible, while simultaneously showing us why it's physically impossible. They exist in the equations as a reminder that the universe's speed limit isn't arbitrary. It's the boundary between two incompatible kinds of reality. Whether tachyons actually exist or not, they serve as a perfect example of how the universe's prohibition against faster-than-light travel isn't just a speed limit. It's a fundamental organizing principle that keeps reality coherent and comprehensible. Imagine folding a piece of paper in half and then poking a pencil through both layers. You've just created a shortcut, a path that connects two distant points on the paper's surface through a route that doesn't exist on the surface itself. This simple demonstration illustrates one of the most intriguing possibilities in theoretical physics: wormholes. A wormhole is a hypothetical tunnel through space-time that connects distant regions of the universe. Unlike faster-than-light travel, which violates the speed limit directly, wormholes would allow you to travel between distant points without ever exceeding the speed of light locally. You would be taking a shortcut through the higher dimensional fabric of space-time itself. The mathematics of wormholes emerges naturally from Einstein's equations. In 1935, Einstein and Nathan Rosen published a paper describing what are now called Einstein-Rosen bridges, hypothetical connections between different parts of space-time. These bridges would appear as tunnels that could, in principle, allow travel between distant regions of the universe. Picture space-time as a vast, flexible membrane, which normally, to travel from one point to another, you must follow the surface of this membrane, respecting the speed of light limit. Speed is for a serve, but a wormhole would be like a tube that connects two distant parts of the membrane, allowing you to take a shortcut through the higher dimensional space in which the membrane exists. The geometry of a wormhole would be extraordinary. At the entrance, space-time would curve inward, creating what physicists call a throat, a narrow tunnel through the higher dimensional space. At the other end, space-time would curve outward again, creating an exit in a distant part of the universe. From the outside, a wormhole might look like a black hole, a region where space-time is so severely curved that not even light can escape. But unlike a black hole, a wormhole would have two mouths, one at each end of the tunnel. You could enter one mouth and emerge from the other, potentially after traveling across vast distances. The travel time through a wormhole would depend on the length of the tunnel. not the distance between the mouths in normal space. You could potentially travel from Earth to the center of the galaxy in minutes, not thousands of years, by taking a shortcut through the wormhole tunnel. But wormholes come with severe problems. The first is stability. The natural tendency of space-time is to collapse wormhole tunnels, crushing them out of existence before anything can pass through. To keep a wormhole open, you would need something with negative energy density, a form of exotic matter that pushes space-time apart rather than pulling it together. This exotic matter would have properties that seem to violate our understanding of physics. It would have negative mass, negative energy, and would exert a repulsive gravitational force. Such matter has never been observed, and it may not be possible for it to exist in quantities large enough to stabilize a wormhole. Even if you could stabilize a wormhole, there would be the problem of causality. If you could travel through a wormhole faster than light could travel through normal space, you would arrive at your destination before light from your departure point. This would create the same causality paradoxes we've explored with faster-than-light travel. The concept of traversable wormholes was developed by physicists like Kip Thorne and Michael Morris. They showed that, in principle, wormholes could be engineered to allow safe passage. But the engineering requirements are staggering. You would need to manipulate space-time itself using exotic matter with precisely controlled properties. There's also the quantum problem. Quantum fields would behave strangely near wormholes, potentially creating feedback loops that would destroy the wormhole as soon as you try to use it. The quantum vacuum itself might become unstable, creating energy densities that would collapse the tunnel. Some physicists have proposed that wormholes might naturally exist at the quantum level. In the foam of space-time, at the smallest scales, tiny wormholes might constantly pop in and out of existence. These microscopic tunnels would be far too small for travel, but they might influence the behavior of particles and fields in subtle ways. The concept of wormholes also raises questions about the topology of space-time. If wormholes exist, then space-time would not be simply connected. It would have a complex, multiply-connected structure with shortcuts and tunnels connecting distant regions. The universe would be like a vast subway system, with hidden passages linking far-flung stations. Perhaps most intriguingly, wormholes might allow for time travel. If you could move one mouth of a wormhole at high speed while keeping the other mouth stationary, time dilation would cause the two mouths to become desynchronized. You could enter one mouth and emerge from the other in your own past, creating all the paradoxes associated with time travel. The search for wormholes has been both theoretical and observational. While no direct evidence has been found, some physicists have proposed that certain astronomical objects might be wormhole mouths. The signatures would be subtle, perhaps unusual gravitational lensing effects or unexpected spectral properties. Wormholes represent a tantalizing loophole in the universe's prohibition against faster-than-light travel. They show us that it might be possible to travel between distant parts of the universe without violating the speed of light locally, but they also show us that such travel would require exotic conditions that may not exist in our universe. Whether wormholes actually exist or not, they serve as a perfect example of how the universe's apparent limitations might be circumvented through clever manipulation of space-time itself. They remind us that the cosmos is far stranger and more flexible than our everyday experience suggests. History. In 1994, a Mexican physicist named Miguel Alcubierre proposed one of the most ingenious loopholes in the universe's speed limit. His idea was elegantly simple. Instead of moving through space-time, why not move space-time itself? The Alcubierre drive would contract space in front of a spacecraft and expand it behind, creating a warp bubble that could travel faster than light while keeping the spacecraft stationary within it. Imagine you're standing on a moving walkway at an airport. You're not walking, but you're still moving because the walkway beneath you is moving. The Alcubierre drive would work on a similar principle, but instead of moving a walkway, it would move space-time itself. The mathematics of the Alcubierre drive emerge from Einstein's equations, which describe how mass and energy curve space-time. Normally, We think of mass and energy as being influenced by spacetime's curvature. But Einstein's equations are symmetric. They also describe how mass and energy can influence spacetime's curvature. The Alcubierre drive would create a specific pattern of spacetime curvature. In front of the spacecraft, spacetime would be compressed, bringing distant regions closer together. Behind the spacecraft, spacetime would be expanded, pushing regions farther apart. The spacecraft would ride the boundary between these regions, surfing on a wave of curved spacetime. From the perspective of someone inside the spacecraft, nothing unusual would happen. There would be no acceleration, no time dilation, no increase in mass. The spacecraft would remain stationary within its local region of spacetime. But from the perspective of the outside universe, the spacecraft would be moving faster than light. This is the beautiful cleverness of the Alcubierre drive. It doesn't violate the speed of light limit, because the spacecraft never actually moves faster than light through spacetime. Instead, spacetime itself moves, carrying the spacecraft along like a cosmic conveyor belt. The energy requirements for an Alcubierre drive are, unfortunately, astronomical. Early calculations suggested that you would need more energy than exists in the observable universe. The drive would require exotic matter with negative energy density, the same kind of exotic matter needed to stabilize wormholes. This exotic matter would need to have properties that seem to violate our understanding of physics. It would exert a repulsive gravitational force, pushing spacetime apart rather than pulling it together. Such matter has never been observed, and it may not be possible for it to exist in the quantities required. But physicists have worked to reduce the energy requirements. By optimizing the shape of the warp bubble and the distribution of exotic matter, they've managed to reduce the energy requirements from universe scale to merely star scale, still impossibly large, but progress nonetheless. The Alcubierre drive would also face the problem of causality. If you could travel faster than light, even by warping spacetime, you would still arrive at your destination before light from your departure point. This would create the same causality paradoxes we've explored with other forms of faster-than-light travel. There's also the problem of control. How would you steer an Alcubierre drive? How would you start and stop it? The drive would need to manipulate spacetime itself, using exotic matter with precisely controlled properties. The engineering challenges are staggering. Quantum effects would also be problematic. The quantum vacuum would respond to the extreme spacetime curvature around the drive, potentially creating feedback loops that would destroy the warp bubble. The energy densities required might exceed the limits at which spacetime itself remains stable. Perhaps most troubling is the problem of horizon formation. The extreme curvature of spacetime around an Alcubierre drive might create event horizons, regions, where spacetime becomes so curved that information cannot escape. The spacecraft might become causally disconnected from the outside universe. There's also the question of what happens to the spacetime left behind. The Alcubierre drive would leave a trail of distorted spacetime in its wake, potentially creating gravitational waves and other effects that would propagate throughout the universe. The environmental impact of warp drive travel might be enormous. Some physicists have proposed that the Alcubierre drive might be subject to quantum limitations. The uncertainty principle might prevent the precise control of exotic matter required for the drive. Quantum fluctuations might disrupt the warp bubble, making faster-than-light travel impossible even in principle. Recent research has explored modifications to the Alcubierre drive that might reduce its energy requirements or eliminate the need for exotic matter. These modifications involve changing the shape of the warp bubble or using different space-time geometries. While promising, these approaches still face enormous theoretical and practical challenges. The Alcubierre drive has also inspired research into other forms of warp drive. Physicists have proposed bubble drives, wormhole drives, and other exotic propulsion systems that would manipulate spacetime itself. Each approach faces its own set of challenges and limitations. Perhaps most intriguingly, the Alcubierre drive has led to research into the fundamental nature of spacetime itself. If spacetime can be warped and manipulated, what does this tell us about the nature of reality? Are space and time fundamental, or are they emergent properties of something deeper? The Alcubierre drive represents the ultimate engineering challenge, the manipulation of space-time itself. It shows us that faster-than-light travel might be possible without violating the speed of light limit, but it also shows us that such travel would require capabilities that are far beyond our current understanding of physics. Whether the Alcubierre drive will ever be built or not, it serves as a perfect example of how theoretical physics can inspire us to think beyond our current limitations. Outwith the chakaf, outwith the toth and no shu or fithia, might was prith and doster. It reminds us that the universe is far stranger and more flexible than we might imagine, and that the impossible might simply be the not yet possible. Let's descend into the quantum realm, where particles behave in ways that seem to mock our understanding of space, time, and the speed of light. Here, in the microscopic world that underlies all reality, we encounter phenomena that appear to violate the cosmic speed limit in the most subtle and profound ways. Quantum entanglement is perhaps the most mystifying of these phenomena. When two particles become entangled, they form a single quantum system, even when separated by vast distances. Measure one particle, and you instantly know something about its partner, regardless of how far apart they are. This connection seems to operate faster than light, creating what Einstein famously called spooky action at a distance. Imagine two coins that are quantumly entangled. In the normal world, each coin would be either heads or tails, independent of the other. But entangled quantum coins exist in a superposition. They're both heads and tails simultaneously until you observe them. When you finally look at one coin and find it heads, you instantly know that the other coin, no matter how far away, must be tails. This instantaneous correlation seems to violate the speed of light limit. If you measure one particle on Earth, and its entangled partner is near Alpha Centauri, the correlation appears to be established faster than light could travel between them. Information about the measurement seems to propagate instantly across the 4 light-years of space. This centrates entangled to Merian, the formus of Ligspeedin Narian. This centrates entangled to Merian, the formus of Ligspeedin Narian. But here's where quantum mechanics becomes beautifully subtle. While the correlation is instantaneous, no information actually travels between the particles. You can't use entanglement to send messages faster than light, because the measurement results are random. You can't control what result you'll get when you measure your particle, so you can't encode information in the measurement. Think of it this way. Imagine you and a friend each have one of a pair of magic coins. When you flip your coin, it comes up heads or tails randomly. But whatever your coin shows, your friend's coin will always show the opposite. The correlation is perfect and instantaneous, but you can't use it to communicate because you can't control what your coin will show. This is the paradox of quantum entanglement. It creates correlations that seem to violate the speed of light limit, but it does so in a way that preserves the fundamental prohibition against faster-than-light information transfer. The universe has found a way to be both mysterious and consistent. The mathematics of entanglement involves what physicists call the wave function, a mathematical description of all possible states of a quantum system. For entangled particles, the wave function cannot be separated into independent parts. The particles exist as a single unified system, regardless of the distance between them. When you measure one particle, you cause the wave function to collapse, instantly determining the states of both particles. This collapse seems to happen instantaneously, but it's not a physical process in the usual sense. No energy or information travels between the particles. Instead, the wave function is a mathematical description of reality that transcends our usual notions of space and time. The experimental verification of entanglement has been one of the triumphs of modern physics. Scientists have created entangled particles and separated them by ever-increasing distances, confirming that the correlations persist regardless of separation. The spooky action is real, even though no action in the usual sense actually occurs. But entanglement raises profound questions about the nature of reality. If particles can be correlated instantaneously across vast distances, what does this tell us about the nature of space and time? Are they fundamental aspects of reality, or are they emergent properties of something deeper? Some interpretations of quantum mechanics suggests that entanglement reveals the non-local nature of reality. In this view, the universe is fundamentally interconnected, with all quantum systems forming a single, unified whole. Space and time are illusions created by our limited perspective on this deeper reality. Other interpretations suggest that entanglement doesn't violate locality at all. In the many worlds interpretation, for example, measurement doesn't cause the wave function to collapse. Instead, all possible outcomes occur in parallel universes. The correlations we observe are just the result of living in one particular branch of the universal wave function. The phenomenon of quantum entanglement also raises questions about causality. If correlations can be established instantaneously, what does this mean for the relationship between cause and effect? Are there aspects of reality that transcend our usual understanding of causality? This phenomenon of quantum entanglement also raises questions about causality. If correlations can be established instantaneously, this phenomenon of causality, perhaps most intriguingly, entanglement might provide insights into the nature of consciousness itself. Some physicists have proposed that consciousness might be a quantum phenomenon, with entangled particles in the brain creating the unified experience of awareness. If true, this would suggest that consciousness itself might operate according to principles that transcend the speed of light limit. The practical applications of entanglement are beginning to emerge. Quantum computers use entanglement to perform calculations that would be impossible for classical computers. Quantum cryptography uses entanglement to create unbreakable codes. Quantum teleportation uses entanglement to transfer quantum states across distances. But these applications still respect the speed of light limit. Quantum teleportation doesn't allow faster-than-light travel. It transfers quantum states, not objects. Quantum cryptography doesn't allow faster-than-light communication. It allows secure communication at normal speeds. These applications still respect the speed of light limit. Quantum entanglement shows us that the universe is far stranger than our everyday experience suggests. It reveals phenomena that seem to violate our understanding of space, time, and causality, while simultaneously respecting the fundamental laws of physics. It's a reminder that the quantum realm operates according to principles that transcend our usual notions of reality. Deep in the quantum realm, there exists a fundamental limitation that shapes the very nature of reality, the uncertainty principle. This principle, first articulated by Werner Heisenberg in 1927, tells us that certain pairs of properties cannot be simultaneously measured with perfect precision, but its implications extend far beyond measurement. It reveals something profound about the nature of existence itself and may hold keys to understanding faster-than-light phenomena. The most famous version of the uncertainty principle deals with position and momentum. The more precisely you try to determine where a particle is, the less precisely you can know how fast it's moving. This isn't just a limitation of our measuring instruments. It's a fundamental feature of reality. The universe itself seems to be built on a foundation of inherent uncertainty. But there's another form of the uncertainty principle that's particularly relevant to our exploration of faster-than-light travel, the energy-time uncertainty relation. This tells us that the more precisely we try to determine the energy of a system, the less precisely we can know when that energy measurement occurs. Conversely, if we want to know the exact timing of an event, we must accept uncertainty in the energy involved. This energy-time uncertainty creates fascinating possibilities. For very short periods of time, the universe allows violations of energy conservation. Virtual particles can pop into existence from nothing, borrow energy from the vacuum, and then disappear before the universe's accounting system notices. These quantum fluctuations are not just theoretical. They have measurable effects on the behavior of atoms and the properties of the vacuum itself. Now, here's where things get intriguing for faster-than-light travel. The uncertainty principle might allow particles to briefly exceed the speed of light during these quantum fluctuations. If a particle can borrow energy from the vacuum, it might be able to use that energy to travel faster than light for infinitesimally short periods or distances. Ears were twisting this. This is the realm of quantum tunneling, where particles can pass through barriers that should be impenetrable according to classical physics. An electron can tunnel through a barrier instantly, regardless of the barrier's width. This seems to violate the speed of light limit, but the uncertainty principle provides a loophole. The math becomes beautifully complex here. The tunneling process involves wave functions that extend beyond the barrier, creating what physicists call evanescent waves. These waves decay exponentially with distance, but they can reconnect on the other side of the barrier, allowing the particle to appear on the far side without ever existing in the barrier itself. Some experiments have suggested that quantum tunneling might occur faster than light. Photons tunneling through barriers have been observed to emerge earlier than they would if they had traveled through empty space at light speed. This has led to speculation about using quantum tunneling for faster-than-light communication. But here's the catch. The uncertainty principle gives with one hand while taking away with the other. While it might allow faster-than-light travel for quantum processes, it also prevents us from using these processes to send information faster than light. The randomness inherent in quantum mechanics means that we can't control the tunneling process precisely enough to encode information in it. The uncertainty principle also affects our understanding of the vacuum itself. What we think of as empty space is actually filled with quantum fluctuations, virtual particles that constantly pop in and out of existence. These fluctuations respect the uncertainty principle, borrowing energy from the vacuum and paying it back before the universe notices. But some of these virtual particles might be tachyons, faster-than-light particles that exist only in the quantum foam. These virtual tachyons would have imaginary mass and would exist for such short periods that they couldn't be directly observed. But they might influence the behavior of normal particles in subtle ways. The uncertainty principle might also provide a mechanism for the universe to protect itself from causality violations. If faster-than-light travel were possible, it could create paradoxes where effects precede causes. But the uncertainty principle might prevent these paradoxes by making it impossible to control faster-than-light processes precisely enough to create causal loops. Think of it as a cosmic censorship mechanism. The universe allows faster-than-light phenomena at the quantum level, but it prevents us from using these phenomena to violate causality. The randomness of quantum mechanics serves as a firewall against paradoxes. The uncertainty principle also has implications for consciousness and observation. The act of measurement causes quantum wave functions to collapse, determining the properties of particles. But this collapse might itself be a faster-than-light process, instantly determining the state of entangled particles, regardless of their separation. Some physicists have proposed that consciousness itself might be a quantum phenomenon that operates according to the uncertainty principle. If true, this would suggest that awareness might transcend the normal limitations of space and time, operating in a realm where the speed of light limit is more flexible. The uncertainty principle reveals that the universe is built on a foundation of fundamental uncertainty. This uncertainty isn't a bug. It's a feature that allows for the rich complexity of quantum phenomena while preventing violations of causality. It creates a universe that is both mysterious and stable, both unpredictable and consistent. Perhaps most profoundly, the uncertainty principle suggests that the universe's prohibition against faster-than-light travel isn't absolute. There are loopholes, quantum exceptions, and brief moments where the normal rules are suspended. But these exceptions are carefully controlled by the inherent randomness of quantum mechanics, ensuring that the universe remains logically consistent. The uncertainty principle shows us that the quantum realm operates according to principles that transcend our everyday understanding of reality. It reveals a universe where faster-than-light phenomena might be possible, but only in ways that preserve the fundamental structure of causality and logic. In our journey through the quantum realm, we encounter a subtle but profound distinction that may hold the key to understanding faster-than-light phenomena, the difference between information and matter. This distinction reveals that the universe might treat these two fundamental aspects of reality very differently when it comes to the speed of light limit. Let's begin with matter, the stuff of atoms, molecules, and everything we can touch and see. We've explored how matter faces seemingly insurmountable barriers to faster-than-light travel, infinite energy requirements, infinite mass increase, and the breakdown of causality. These barriers seem absolute and unforgiving. But information is different. Information is abstract. It's not made of particles or waves, but rather represents the arrangement and relationships between physical systems. When you read these words, you're not absorbing matter from the page. You're absorbing information about the ideas I'm trying to convey. In the quantum realm, this distinction becomes crucial. Quantum entanglement, as we've seen, creates correlations between particles that seem to operate instantaneously across any distance. While no matter travels between entangled particles, information about their correlated states appears to be shared instantly. Consider the famous thought experiment of quantum teleportation. This process doesn't actually move particles from one location to another. It transfers the quantum state of one particle to another particle in a distant location. The information about the particle's state travels, but the particle itself remains where it is. The mathematics of quantum teleportation reveals something fascinating. While the information transfer appears to be instantaneous, the process still respects the speed of light limit. The person receiving the teleported state can't access the information until they receive classical information about the measurement, and this classical information must travel at light speed or slower. This suggests that the universe makes a distinction between different types of information, quantum information. The abstract mathematical relationships between particles might be able to transcend the speed of light limit, but classical information, the kind we can use to communicate and make decisions, remains bound by the cosmic speed limit. The concept of information also appears in the context of black holes. Stephen Hawking's work on black hole radiation revealed that black holes emit information as they evaporate. But this information is encoded in incredibly subtle quantum correlations that would take longer than the age of the universe to decode. The information escapes the black hole, but it does so in a way that's practically useless. This raises profound questions about the nature of information itself. Is information fundamental to reality, or is it an emergent property of matter and energy? Some physicists propose that information might be more fundamental than matter, that the universe is essentially computational, with matter and energy in different ways of processing information. The concept of computational complexity adds another layer to this discussion. Even if information could travel faster than light, the processing of that information might be limited by other factors. The universe might have a maximum rate at which information can be processed, regardless of how fast it can travel. Consider the quantum vacuum itself. The vacuum is filled with information. It contains virtual particles, quantum fluctuations, and the potential for matter to spontaneously appear. This information about the vacuum's state seems to be non-local, existing everywhere simultaneously. But accessing this information requires physical processes that respect the speed of light limit. The distinction between information and matter also appears in the context of quantum computing. Quantum computers use entanglement to process information in ways that seem to violate classical limitations. They can perform certain calculations exponentially faster than classical computers, but they still can't solve problems that require faster than light information transfer. Perhaps most intriguingly, the distinction suggests that consciousness itself might be informational rather than material. If consciousness is the processing of information rather than the physical activity of brain cells, then it might operate according to different rules than matter. This could explain phenomena like intuition, creativity, and the sense of unity that people report in mystical experiences. The relationship between information and causality is also complex. In the normal world, information about causes must travel to effects at light speed or slower. But in the quantum realm, information about correlations seems to be established instantly. This suggests that there might be different types of causality: local causality that governs matter and energy, and non-local causality that governs information. The universe's apparent distinction between information and matter might also explain why faster-than-light travel seems impossible for matter, but possible for certain types of information. Matter has energy, momentum, and mass. properties that are constrained by the geometry of space-time. But information is abstract and might not be subject to these same constraints. This distinction also has implications for our understanding of time. Matter moves forward through time, aging and evolving according to the laws of thermodynamics. But information might be temporal in a different way. It might exist in a kind of timeless realm where past, present, and future are all equally accessible. The search for faster-than-light phenomena might therefore be focused on the wrong target. Instead of trying to accelerate matter beyond the speed of light, we might need to focus on manipulating information itself. This could involve quantum entanglement, quantum tunneling, or other quantum phenomena that allow information to transcend the normal limitations of space and time. The distinction between information and matter reveals that the universe might be more flexible than we imagine. While matter seems to be strictly bound by the speed of light limit, information might operate according to different, more permissive rules. This suggests that the future of faster-than-light phenomena might lie not in the realm of spaceships and rockets, but in the realm of quantum information and consciousness itself. Imagine a universe where the speed of light is not the ultimate barrier, where life itself could evolve to transcend this cosmic speed limit. What would biology look like in such a realm? How would living systems adapt to the strange physics of faster-than-light existence? Tonight, let's explore the beautiful impossibility of life beyond the ultimate speed limit. In our universe, biology is intimately connected to the speed of light. Every biochemical reaction, every neural impulse, every cellular process depends on electromagnetic interactions that propagate at light speed. The very structure of DNA, the folding of proteins, the operation of cell membranes, all of these depend on the fundamental constants of physics, including the speed of light. But in a faster-than-light universe, these constraints would be different. Life might evolve mechanisms that operate faster than light, creating biological systems that could process information, respond to stimuli, and adapt to changes at superluminal speeds. On a per the second trace he is de fer. The very concept of reaction time would be transformed. Consider the nervous system. In our world, neural impulses travel at speeds far below light speed, typically around 100 meters per second. This limits how quickly organisms can respond to their environment. But in a faster-than-light universe, neural networks might evolve that operate at superluminal speeds, creating consciousness that could think and react faster than light itself. The implications for intelligence would be profound. Thought processes that take milliseconds in our world might occur in negative time in a faster-than-light universe. An organism might be able to predict events before they happen, not through precognition, but through the natural operation of a nervous system that operates faster than the causal signals that create those events. But this creates paradoxes. If an organism could think faster than light, it might be able to observe its own future thoughts. It could make decisions based on knowledge of decisions it hasn't made yet. The very concept of free will would become temporarily scrambled. The evolution of such organisms would also be paradoxical. Natural selection operates through the differential survival and reproduction of organisms over time. But in a faster-than-light universe, the temporal order of cause and effect would be scrambled. Organisms might evolve in response to future selection pressures, or they might prevent their own evolution by adapting to conditions that their adaptation itself prevents. The biochemistry of faster-than-light life would require exotic physics. Molecular interactions would need to operate faster than light, perhaps through quantum entanglement or other non-local quantum phenomena. The very atoms that compose living systems might need to have properties that transcend our current understanding of chemistry. Consider photosynthesis, the process by which plants convert light into chemical energy. In our world, this process is limited by the speed at which photons can be absorbed and processed. But in a faster-than-light universe, organisms might evolve to harvest energy from superluminal processes, perhaps tapping into the exotic matter or negative energy that would be required to exceed the speed of light. The ecology of a faster-than-light universe would be bizarre. Predator-prey relationships would be complicated by the fact that predators might be able to catch prey, before the prey realizes it's being hunted. Communication between organisms might involve faster-than-light signals, creating social structures that span vast distances instantaneously. But perhaps the most profound change would be in the organism's relationship with time itself. In our world, aging is driven by entropy, the natural tendency of systems to become more disordered over time. But in a faster-than-light universe, the thermodynamic arrow of time might be reversed. Organisms might become younger as they age, or they might exist in a state where aging has no meaning. The reproductive biology of faster-than-light organisms would be paradoxical. Reproduction involves the transfer of genetic information from parents to offspring over time. But in a faster-than-light universe, offspring might exist before their parents, or genetic information might flow backward in time, creating evolutionary paradoxes. The sensory systems of such organisms would need to operate in ways that transcend our understanding of perception. Vision, for example, relies on the detection of light that has traveled from objects to the eye. But in a faster-than-light universe, organisms might be able to see events before they happen, or they might perceive light that is traveling backward in time. The concept of memory would also be transformed. Memory involves the storage and retrieval of information about past events. But in a faster-than-light universe, organisms might remember events that haven't happened yet, or they might forget events that are happening now. The very concept of personal identity, which depends on the continuity of memory, would become problematic. Perhaps most intriguingly, consciousness itself might transcend the normal limitations of space and time. If consciousness is an information processing phenomenon, and if information can travel faster than light, then consciousness might be able to exist in a distributed, non-local form. An organism might be conscious of events happening in distant parts of the universe simultaneously. The death of faster-than-light organisms would also be paradoxical. In our world, death is the irreversible cessation of biological processes. But in a faster-than-light universe, the concept of irreversibility becomes meaningless. Builty inturers, 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 insurers. Organisms might be able to die before they're born, or they might be able to reverse their own death through faster-than-light processes. The very concept of species would be challenged. Species are typically defined by their ability to interbreed and produce fertile offspring. But in a faster-than-light universe, organisms might be able to interbreed with their own ancestors or descendants, creating temporal species that exist across multiple time periods simultaneously. Biology beyond light speed would represent more than just faster life. It would be life that transcends the normal relationships between cause and effect, between past and future, between self and environment. It would be life that exists in the strange realm where the normal rules of existence are turned upside down. Imagine a civilization where information travels faster than light. The implications would be so profound that they would fundamentally reshape every aspect of society, culture, and human interaction. Let's explore what communication and civilization might look like in a universe where the cosmic speed limit no longer applies to information exchange. In our current universe, the speed of light creates natural barriers to communication. A message sent from Earth to Mars takes between 4 and 24 minutes to arrive, depending on the planet's positions. A message to the nearest star takes over 4 years. These delays have profound implications for any interstellar civilization. They create islands of causality, where each world must largely govern itself, because real-time communication is impossible. But in a faster-than-light universe, these barriers would dissolve. Imagine being able to have a real-time conversation with someone on a planet orbiting Alpha Centauri. You could ask a question and receive an answer immediately, creating a truly galactic society where distance becomes irrelevant to social interaction. The political implications would be staggering. In our world, the vastness of space naturally creates independence. Distant colonies must be self-governing because they can't communicate with their home world quickly enough for centralized control. But with faster-than-light communication, a single government could theoretically control an entire galaxy, making decisions on a central world and implementing them instantly across thousands of star systems. This would create new forms of democracy and governance. Citizens on distant worlds could participate in real-time voting, creating a truly galactic democracy where every voice could be heard instantly. Political movements could span the galaxy, with ideas and revolutions spreading at superluminal speeds. The economic implications would be equally profound. In our world, trade across interstellar distances is limited by the time it takes to communicate orders, prices, and market conditions. But with faster-than-light communication, a truly galactic economy could emerge. Stock markets could operate across the galaxy, with prices and trades executed instantaneously across vast distances. But this would also create new vulnerabilities. Economic bubbles and crashes could propagate across the galaxy faster than light, creating systemic risks that span multiple star systems. The concept of economic isolation, where distant worlds are protected from economic shocks by the speed of light, would disappear. The social implications would be perhaps the most profound. Human relationships are shaped by the constraints of communication. In our world, long-distance relationships are challenging because of the delays in communication. But with faster-than-light communication, true intimacy could be maintained across galactic distances. Families could remain close, even when separated by hundreds of light years. This would create new forms of community and belonging. People could participate in social groups that span the galaxy, creating communities of interest that transcend planetary boundaries. The concept of local community, people who live near each other, might become less important than communities of choice that exist across vast distances. This would create new forms of community and belonging. The cultural implications would be enormous. In our world, distance creates cultural diversity. Isolated populations develop their own languages, customs, and ways of life. But with faster-than-light communication, cultural homogenization might occur on a galactic scale. Trends, fashions, and ideas could spread instantly across the galaxy, creating a unified galactic culture. But this could also lead to cultural resistance movements. Some populations might deliberately choose to limit their faster-than-light communications, creating intentional islands of cultural isolation. The choice to communicate at light speed might become a form of cultural rebellion against galactic homogenization. The educational implications would be revolutionary. In our world, access to education is limited by geography and resources. But with faster-than-light communication, anyone in the galaxy could access the best educational institutions instantly. A student on a frontier world could attend lectures at the Galactic Center, participate in real-time discussions with the greatest minds in the galaxy, and access any library or database instantly. This would create unprecedented opportunities for human development and learning, but it would also create new forms of inequality. Those with access to faster-than-light communication would have enormous advantages over those without, creating a galactic digital divide that could span star systems. The psychological implications would be equally profound. Human psychology is adapted to the constraints of light-speed communication. We form attachments to people we can interact with regularly, and we develop a sense of place based on our immediate environment. But with faster-than-light communication, these psychological foundations might be challenged. People might develop multiple simultaneous relationships across the galaxy, creating new forms of attachment and intimacy. The concept of home might become more fluid, as people could maintain meaningful connections with multiple worlds simultaneously. In Forbingfeses, in neuther simultaneouses. But this might also lead to psychological fragmentation. If someone can be simultaneously present in multiple conversations across the galaxy, what does it mean to be a unified self? The human mind, evolved for local interactions, might struggle with the cognitive demands of galactic-scale communication. The concept of privacy would also be transformed. In our world, distance provides natural privacy. What happens on one world is unknown to others, until light-speed signals carry the information. But with faster-than-light communication, privacy might become a more precious and fragile resource. Information about events could spread across the galaxy instantly, making it difficult to maintain local privacy. Perhaps most profoundly, faster-than-light communication would create a civilization that exists in a kind of eternal present. In our world, the speed of light creates a natural historical record. We can look at distant galaxies and see them as they were in the past. But with faster-than-light communication, the entire galaxy would exist in a synchronized now, creating a civilization that lives in real time across vast distances. This would fundamentally change how we understand time, history, and causality. The past would no longer be a distant country, accessible only through historical records. It would be a living, breathing part of the present, accessible through faster-than-light communication with our earlier selves. The most profound consequence of faster-than-light communication would be the end of cosmic isolation, the vast loneliness that separates worlds and civilizations across the universe. For the first time in cosmic history, intelligence would be able to transcend the barriers of space and time, creating a truly connected universe where no mind would ever be truly alone. In our current universe, isolation is built into the fabric of space-time itself. Each world is an island of consciousness, surrounded by years, decades, or centuries of silence. When we send a message to another star system, we're essentially throwing a bottle into a cosmic ocean, hoping that someone will find it and understand. The civilizations that might exist around other stars are as unreachable as if they existed in parallel dimensions. This isolation has profound implications for the development of intelligence. Each civilization must solve the fundamental problems of existence independently. The wheel must be invented countless times. Mathematics must be discovered again and again. And the great questions of philosophy and science must be approached fresh by each isolated mind. But in a faster-than-light universe, this isolation would end. Imagine the first moment when a faster-than-light signal reaches Earth from another star system. Not just a signal, but a message, a greeting, a recognition that we are not alone. The psychological impact would be unprecedented. Humanity would suddenly find itself part of a vast community of intelligence spanning the galaxy. The sharing of knowledge would be instantaneous and universal. Scientific discoveries made on one world could be transmitted instantly to all others. A mathematical theorem proved on a planet orbiting Vega could be verified and expanded upon by minds on worlds orbiting Arcturus within moments. The collective intelligence of the galaxy would become truly collective, with each mind contributing to and benefiting from the knowledge of all others. This would create an unprecedented acceleration in the development of intelligence. Problems that would take centuries for an isolated civilization to solve could be resolved in moments through the collaborative efforts of minds across the galaxy. The barriers between individual intelligences would begin to dissolve as knowledge flowed freely at superluminal speeds. But this connectivity would also create new forms of vulnerability. In our isolated universe, the destruction of one world doesn't directly affect others, but in a connected universe, the loss of one node in the network could have cascading effects throughout the galactic community. The failure of a single civilization could potentially bring down the entire network of galactic intelligence. The concept of individual identity would be challenged in unprecedented ways. If thoughts, memories, and experiences can be shared instantaneously across the galaxy, what does it mean to be an individual mind? The boundaries between self and other would become fluid, as consciousness itself becomes distributed across multiple worlds and bodies. Imagine being able to share not just words or images, but direct experiences. The feeling of standing on an alien world, the sensation of seeing a double sunset, the emotional impact of discovering a new form of life. The barriers between minds would dissolve as experience itself becomes shareable across vast distances. This would create new forms of empathy and understanding. Conflicts that arise from misunderstanding or inability to comprehend another's perspective would become impossible when minds can directly share experiences. The galactic community would develop a kind of collective consciousness, where the suffering of one world is felt by all, and the joy of discovery is shared universally. But this might also lead to the homogenization of thought. If ideas can spread instantly across the galaxy, local variations in thinking might disappear. The rich diversity of isolated civilizations, each developing its own unique approach to existence, might be lost in favor of a uniform galactic mindset. The concept of creativity, Sao, would be transformed. In our world, creativity often emerges from the unique perspective of isolated minds working independently. But in a connected universe, creativity might become a collaborative process where ideas are built upon and refined by minds across the galaxy in real time. The search for meaning and purpose would take on new dimensions. In our isolated universe, each civilization must find its own reason for existence. But in a connected universe, purpose might become collective, a shared mission that spans the galaxy and involves all conscious beings working together toward common goals. The relationship between consciousness and the universe itself would be transformed. In our world, consciousness seems to be a rare and precious phenomenon, isolated on scattered worlds throughout the cosmos. But in a faster-than-light universe, consciousness might become a truly cosmic phenomenon, spanning the galaxy and eventually the universe itself. This might lead to the emergence of something unprecedented, a galactic consciousness that transcends individual minds while still encompassing them. This wouldn't be the loss of individual identity, but rather the expansion of identity to include the entire galactic community. The end of isolation would also transform our understanding of death and mortality. In our world, the death of an individual, or even an entire civilization, is a permanent loss. But in a connected universe, the thoughts, memories, and experiences of individuals could be preserved and shared across the galactic network. Death might become not an ending, but a transformation, emerging with the greater galactic consciousness. Perhaps most profoundly, the end of isolation would represent the next stage in the evolution of intelligence itself. Just as individual neurons connected to form brains, and individual brains connected to form societies, the connection of civilizations across the galaxy would create a new form of intelligence that transcends anything we can currently imagine. The universe would no longer be a cold, empty void, punctuated by isolated islands of consciousness. Instead, it would become a living, thinking entity, where every mind is connected to every other mind, where knowledge flows freely across vast distances, and where the ancient loneliness of consciousness finally comes to an end. This would be more than just the end of isolation. It would be the beginning of a new chapter in the story of consciousness itself, a chapter where the universe awakens to its own existence through the connected minds of all its conscious beings. In the realm beyond light speed, one of the most profound questions in philosophy becomes even more complex. Do we have free will, or is everything predetermined? The ability to outrun light would create a universe where the very concepts of choice, causation, and moral responsibility become paradoxical in ways that challenge our deepest assumptions about consciousness and existence. Let's begin with how we understand free will in our current universe. We experience ourselves as making choices, deciding what to have for breakfast, choosing which path to take through life, determining how to respond to challenges. These choices feel real and meaningful because they appear to influence the future. We act in the present, and consequences unfold over time, creating a clear arrow of causality from decision to outcome. But in a faster-than-light universe, this clear arrow would become hopelessly tangled. If you could travel faster than light, you could potentially observe the consequences of your choices before you make them. You might see the results of a decision in your future, then return to your present and make that decision based on knowledge of its outcome. Imagine standing at a crossroads, able to travel faster than light down each path to observe where it leads. You see that the left path leads to happiness, the right path to sorrow. You return to the crossroads and choose the left path. But did you really choose freely, or were you simply following a predetermined script written by your future observations? This creates what philosophers call a causal loop. Your future observations influence your present choices, which create the future you observed. It's like a cosmic version of the chicken and egg problem. Which came first, the choice or the knowledge of its consequence? The concept of moral responsibility becomes equally problematic. In our world, we hold people accountable for their actions because we believe they could have chosen differently. But in a faster-than-light universe, if you can observe the consequences of your actions before you take them, are you truly responsible for choices that seem predetermined by your future knowledge? Consider a more complex scenario. You use faster-than-light travel to observe a future where you commit a crime. You see the victims, the consequences, the suffering you cause. You return to your present with this knowledge. Now, do you have the free will to choose not to commit the crime? Or are you trapped in a causal loop where your future actions determine your present knowledge, which compels you to take those future actions? This touches on fundamental questions about the nature of time and causality. In our normal universe, the past is fixed. It cannot be changed. The future is open. It can be influenced by our present choices. But in a faster-than-light universe, these categories become meaningless. If you can observe your future and then influence your past, the entire concept of temporal flow breaks down. The implications for consciousness are profound. Our sense of self is built on the continuity of memory and the ability to make choices that shape our future. But in a faster-than-light universe, you might remember making choices that you haven't made yet, or you might find yourself unable to make choices because you've already observed their outcomes. This creates what philosophers call the problem of temporal personal identity. Are you the same person who made the choice, or are you a different person who observed the outcome? If your past self made a decision based on your future self's observations, which self is really responsible for the choice? The concept of determinism takes on new dimensions in a faster-than-light universe. In our world, determinism suggests that every event is the inevitable result of prior causes. But in a faster-than-light universe, events might be the result of future causes, creating a kind of reverse determinism, where the future determines the past. But perhaps the most disturbing possibility is that faster-than-light travel would create a universe where free will is both impossible and inevitable. You would be free to choose your actions, but only because you've already observed their consequences. You would be determined to make certain choices, but only because you've freely chosen to observe their outcomes. This paradox extends to the concept of knowledge itself. In our world, knowledge is power because it allows us to make better choices. But in a faster-than-light universe, knowledge might be a prison, trapping us in causal loops, where knowing the future compels us to create it. The question of whether free will exists becomes even more complex when we consider the possibility of multiple observers. If multiple people can travel faster than light and observe different possible futures, whose observations determine what actually happens, do we have free will collectively, even if we don't have it individually? Perhaps the most profound implication is that faster-than-light travel would force us to reconsider the very nature of choice itself. In our world, a choice is selecting one possibility from many, but in a faster-than-light universe, all possibilities might exist simultaneously, with choice being merely the selection of which possibility to observe. This suggests that free will and determinism might not be opposing concepts, but rather different perspectives on the same underlying reality. From one perspective, everything is predetermined by the causal loops created by faster-than-light observation. From another perspective, everything is freely chosen by conscious beings who have access to knowledge of all possible outcomes. The philosophical implications of faster-than-light travel would thus extend far beyond physics into the deepest questions of human existence. They would force us to reconsider what it means to be conscious, what it means to choose, and what it means to be morally responsible for our actions in a universe where the normal relationships between cause and effect have been turned upside down. Stepping into the faster-than-light realm would force us to confront the most fundamental question in philosophy: what is the nature of reality itself? Everything we think we know about existence, about what it means for something to be real, about the relationship between observer and observed, about the very foundations of being, would be called into question in ways that are both beautiful and terrifying. In our everyday world, reality seems solid and dependable. Objects exist in definite locations, events happen in a specific order, and the universe maintains a consistent set of physical laws. We can rely on cause and effect, on the flow of time from past to future, on the stability of space and the constancy of physical constants. These form the bedrock of our understanding of what is real. But the faster-than-light realm would reveal these assumptions to be mere approximations, valid only in the limited domain of slower-than-light existence. In the superluminal world, reality would become fluid, contingent, and paradoxical. The very concept of what is real would need to be completely reconsidered. But the faster-than-light realm would reveal these assumptions to be mere approximations, valid only in the limited domain of slower-than-light existence. In the superluminal world, reality would become fluid, contingent, and paradoxical. Consider the nature of objects. In our world, a chair is a chair. It exists in a specific place at a specific time, with definite properties. But in a faster-than-light universe, objects might exist in multiple states simultaneously. A chair might be both broken and whole, both here and there, both existing and non-existing, depending on the perspective of the faster-than-light observer. This isn't just a strange quirk of physics. It's a fundamental challenge to our understanding of existence itself. If objects can exist in contradictory states simultaneously, what does it mean to say that something exists at all? The very category of being would become ambiguous and observer-dependent. The concept of truth would be equally challenged. On our world, truth is typically understood as correspondence to reality. A statement is true if it accurately describes the way things are. But in a faster-than-light universe, the way things are would depend on when and how you observe them. Truth would become relativistic, varying with the observer's position and motion through space-time. This would create a universe where contradictory statements could be simultaneously true. From one faster-than-light perspective, an event might happen. From another perspective, it might not happen. Both perspectives would be equally valid, equally real, equally true. The law of non-contradiction, one of the fundamental principles of logic, would break down. The relationship between mind and reality would become even more complex. In our world, we generally assume that reality exists independently of our observation of it. The universe was here before we evolved to observe it, and it will continue to exist after we're gone. But in a faster-than-light universe, the act of observation would become entangled with the creation of reality itself. If you could travel faster than light to observe events before they happen, your observations might influence those events. Reality would become co-created by the observer and the observed, with no clear boundary between subjective experience and objective existence. Reality, with the savoir accommodation, the universe would become participatory, with consciousness playing a fundamental role in determining what is real. This touches on deep questions about the nature of consciousness itself. If consciousness can travel faster than light, does it exist independently of the physical brain? Is consciousness a fundamental feature of reality, like space and time, or is it an emergent property of complex information processing? In a faster-than-light universe, consciousness might be revealed to be more fundamental than matter itself. The concept of identity would become problematic in ways that challenge our most basic assumptions about selfhood. If you could travel faster than light and observe yourself from multiple perspectives simultaneously, which perspective represents the real you? If you could influence your own past through faster-than-light travel, are you the same person who made the original choices, or are you a different person who exists in a causally connected but temporally scrambled relationship with your past self? The notion of a unified, coherent reality would fragment into multiple incompatible realities. Each faster-than-light observer would have their own version of events, their own understanding of what is real, their own truth. The universe would become a collection of overlapping but distinct realities, each valid from its own perspective. This multiplicity of realities would challenge the very concept of objectivity. Science is based on the assumption that there is an objective reality that can be studied and understood through careful observation and experimentation. But in a faster-than-light universe, objectivity might be impossible. Every observation would be subjective. Every measurement would be relative. Every truth would be contingent. Yet perhaps this apparent chaos would reveal a deeper order. Maybe the fragmentation of reality into multiple perspectives would be like the fragmentation of light into different colors through a prism. Not a destruction of unity, but a revelation of hidden richness and complexity. The faster-than-light realm might show us that reality is far more vast and multifaceted than we ever imagined. The nature of reality in a faster-than-light universe might be fundamentally informational rather than material. If information can travel faster than light, while matter cannot, then information might be more fundamental than matter. Reality might be revealed to be a vast information processing system, with matter and energy being merely different ways of organizing and processing information. This would suggest that the universe is essentially computational, with reality being the ongoing calculation of some vast cosmic algorithm. Consciousness might be the universe's way of experiencing its own computations, and faster-than-light travel might be a way of accessing different parts of this vast computational space. The implications are both humbling and exhilarating. They suggest that reality is far stranger, far more complex, and far more beautiful than we ever imagined. The faster-than-light realm would be more than just a strange place to visit. It would be a mirror that reflects back to us the true nature of existence itself. Perhaps the most profound implications of faster-than-light travel would be for consciousness itself, that mysterious phenomenon of subjective experience that makes us who we are. In the superluminal realm, the very nature of awareness, perception, and the sense of self would be transformed in ways that challenge our deepest assumptions about what it means to be conscious. Let's begin with the relationship between consciousness and time. Our experience of awareness is intimately connected to the flow of time. We remember the past, experience the present, and anticipate the future. This temporal flow creates the narrative continuity that we call personal identity. But in a faster-than-light universe, this temporal flow would become scrambled. Imagine what it would be like to be conscious while traveling faster than light. You might experience memories of events that haven't happened yet, or find yourself forgetting events that are happening now. The stream of consciousness that we take for granted, the continuous flow of thoughts, feelings, and experiences, would become temporally fragmented. This fragmentation would challenge the very concept of personal identity. Are you the same person who remembers the future, or are you a different person who exists in a causally connected but temporally scrambled relationship with your past and future selves? If consciousness can transcend the normal flow of time, what does it mean to be a continuous, coherent self? The nature of perception would also be transformed. In our world, perception is about receiving information from the environment through our senses. Light enters our eyes, sound waves reach our ears, and our brain processes this information to create our experience of the world. But this process is fundamentally limited by the speed of light. We can only perceive events after light has had time to travel from them to us. In a faster-than-light universe, perception might transcend these limitations. You might be able to perceive events before they happen, or see light that is traveling backward in time. The normal relationship between cause and effect in perception would break down. You might see the flash of an explosion before you hear the sound, or observe an object before light has had time to reflect off it. This would create new forms of awareness that we can barely imagine. Precognitive perception might allow you to observe events before they occur, giving you a kind of prophetic vision. Retroactive perception might allow you to observe the past directly, without relying on historical records or traces. But perhaps the most profound transformation would be in the nature of consciousness itself. In our world, consciousness seems to be localized in individual brains. Each person has their own private stream of consciousness, their own subjective experience. But in a faster-than-light universe, consciousness might become non-local. If information can travel faster than light, then different parts of a conscious system might be able to communicate instantaneously across vast distances. This could create distributed consciousness, awareness that exists not in a single location, but spread across multiple places simultaneously. You might be conscious of events happening in distant parts of the universe as directly as you're conscious of events happening in your own body. This distributed consciousness might allow for new forms of shared experience. Instead of communicating through language or symbols, beings might be able to share consciousness directly. You could literally experience another person's thoughts, feelings, and perceptions as if they were your own. The boundary between self and other would become fluid. The implications for empathy and understanding would be profound. In our world, we can only approximate what it's like to be someone else, whole. But with shared consciousness, you could experience exactly what it's like to be another being, their joy, their pain, their perspective on reality. This could create unprecedented levels of understanding and compassion, but it might also create new forms of psychological fragmentation. If consciousness can be distributed across multiple locations and shared between multiple beings, what happens to individual identity? Would you still be you if your consciousness was merged with others? Would you still be you if your consciousness was merged with others? Or would you become part of a collective consciousness that transcends individual identity? The relationship between consciousness and physical reality would also be transformed. In our world, consciousness seems to be produced by the physical activity of the brain, but in a faster-than-light universe, consciousness might be more fundamental than physical reality. If consciousness can transcend the speed of light while matter cannot, then consciousness might be the more basic phenomenon. This would suggest that the universe is fundamentally mental rather than physical. Whole matter and energy might be manifestations of consciousness rather than the other way around. Whole reality might be the dream of some cosmic consciousness, with individual minds being windows into this deeper awareness. The nature of knowledge and understanding would also be transformed. In our world, knowledge is limited by the speed at which information can travel, but in a faster-than-light universe, knowledge might be instantaneous and universal. You might have access to all information in the universe simultaneously, creating a kind of omniscience. But this omniscience might come with a price. The human mind is adapted to processing information at human scales and speeds. Exposure to universal knowledge, traveling at faster-than-light speeds, might overwhelm individual consciousness, creating new forms of mental illness or transformation. Perhaps the most beautiful possibility is that faster-than-light consciousness would reveal the universe to be far more alive and aware than we ever imagined. Instead of being a cold, mechanical system, the cosmos might be revealed to be a vast, thinking entity in which individual consciousness are like cells in a cosmic brain. This would suggest that the evolution of consciousness is not just a local phenomenon on Earth, but a universal process. The universe might be gradually awakening to its own existence through the development of faster-than-light consciousness, with each mind contributing to the cosmic self-awareness. The implications of faster-than-light consciousness would thus extend far beyond individual experience into the deepest questions of cosmic purpose and meaning. They would suggest that consciousness is not an accident of evolution, but a fundamental feature of reality that transcends the normal limitations of space and time. As we near the end of our impossible journey, let's contemplate perhaps the most profound question of all. Why does the speed of light limit exist in the first place? This isn't just a question about physics, it's a question about the deepest architectural principles of reality itself, about why the universe is structured the way it is, and what this reveals about the nature of existence. The speed of light isn't arbitrary. It's not as if the universe could have chosen any speed limit and happened to pick 299,792,458 meters per second. Its speed of light isn't arbitrary, 58 meters per second. This specific speed emerges from the fundamental structure of space-time itself, from the mathematical relationships that govern how space and time are woven together into the fabric of reality. In Einstein's equations, the speed of light appears as a fundamental constant that relates space and time. It's not really the speed of light at all. It's the speed at which space-time itself allows information to propagate. Light travels at this speed, not because it's special, but because it's massless, and therefore forced to travel at the maximum speed that space-time permits. But why does space-time have this particular structure? Why is there a maximum speed at all? The answer might lie in the nature of causality itself. A universe without a speed limit would be a universe where causes and effects could become scrambled, where the logical structure of reality would break down. The speed of light limit might exist to preserve the coherence of existence itself. Think of it this way. The universe needs to maintain a consistent story about itself. Events need to happen in a logical order, with causes preceding effects. Information about events needs to propagate in a way that preserves this logical structure. The speed of light limit ensures that the universe can maintain this consistent narrative. Without this limit, the universe would become a place where contradictions are not just possible, but inevitable. Events could be both caused and uncaused, both real and unreal, both past and future simultaneously. The universe would lose its ability to maintain coherent information about itself. The speed of light limit might also be connected to the nature of information itself. Information theory tells us that information cannot be created or destroyed, only transformed. But in a universe without a speed limit, information could appear to be created from nothing or destroyed without trace. The speed of light limit might be necessary to preserve the conservation of information. There's also a thermodynamic aspect to consider. The second law of thermodynamics tells us that entropy always increases, giving time a clear direction. But in a universe without a speed limit, entropy could decrease, heat could flow from cold to hot, and the arrow of time could reverse. The speed of light limit might be necessary to preserve thermodynamic consistency. Perhaps most profoundly, the speed of light limit might be connected to the nature of existence itself. In quantum mechanics, the act of observation plays a fundamental role in determining reality. But observation requires information to travel from the observed to the observer. The speed of light limit ensures that this information transfer happens in a consistent causal manner. Without this limit, the relationship between observer and observed would become paradoxical. You could observe events before they happen, potentially influencing them through your observation. The universe would become a place where the future determines the past, where consciousness creates reality retroactively. The speed of light limit might also be connected to the nature of consciousness itself. If consciousness is an information processing phenomenon, then it would be subject to the same speed limits as other forms of information. The speed of light limit might be necessary to preserve the coherence of conscious experience. Consider the implications for mathematical consistency. Mathematics depends on logical relationships that must be preserved across space and time. But in a universe without a speed limit, these relationships could become scrambled. Mathematical truths could be both true and false simultaneously, depending on the observer's perspective. The speed of light limit might be the universe's way of ensuring that mathematics remains consistent. It creates a framework within which logical relationships can be preserved, where mathematical truths remain true, regardless of the observer's position or motion. There's also an aesthetic dimension to consider. The speed of light limit creates a universe that is both mysterious and comprehensible, both strange and beautiful. It allows for the existence of horizons, regions beyond which we cannot see or communicate. These horizons create a sense of mystery and wonder that might be essential to the universe's beauty. Without the speed of light limit, the universe would be completely transparent. There would be no hidden regions, no unreachable places, no mysteries to explore. The cosmos would lose much of its beauty and wonder. Perhaps the most profound possibility is that the speed of light limit exists because it's necessary for the universe to be conscious of itself. The universe might be gradually awakening to its own existence through the development of consciousness within it. The speed of light limit might be necessary to preserve the coherence of this cosmic consciousness. In this view, the speed of light limit isn't a limitation at all. It's a feature that makes the universe possible. It's the cosmic architecture that allows for the existence of space, time, matter, energy, information, consciousness, and meaning. Without this limit, none of these things could exist in a coherent form. The speed of light limit might thus be the universe's way of ensuring its own existence. It's the fundamental organizing principle that keeps reality coherent, comprehensible, and beautiful. It's not a barrier to be overcome, but a foundation to be celebrated. Despite the seemingly absolute nature of the speed of light barrier, humanity's quest to understand and potentially transcend it continues with remarkable ingenuity and determination. Scientists around the world are probing the deepest mysteries of physics, searching for loopholes, exceptions, and new understandings that might reveal ways around this cosmic speed limit. The search takes many forms, from purely theoretical work that pushes the boundaries of mathematical physics to experimental investigations that probe the quantum realm for hints of faster-than-light phenomena. Each approach offers its own window into the fundamental nature of reality and the possibility of transcending our current limitations. Theoretical physicists continue to explore the mathematical landscapes of general relativity and quantum mechanics, searching for exotic solutions that might permit faster-than-light travel. The Alcubierre drive, while requiring exotic matter, showed that Einstein's equations don't absolutely forbid faster-than-light travel under all circumstances. This has inspired researchers to look for other geometric solutions that might be more physically realizable. Recent work has focused on reducing the energy requirements for warp drives, optimizing their geometry, and exploring whether quantum effects might provide the exotic matter needed. While the challenges remain enormous, each theoretical advance brings us closer to understanding the fundamental limits of what's possible. Experimental physicists are investigating quantum phenomena that seem to violate the speed of light limit in subtle ways. Quantum tunneling experiments have shown particles apparently crossing barriers faster than light. While these experiments don't violate causality, they reveal aspects of quantum mechanics that we don't fully understand and that might point toward new possibilities. The study of quantum entanglement continues to reveal non-local correlations that seem to operate instantaneously across any distance. While these correlations can't be used for faster-than-light communication, they suggest that the universe has non-local aspects that transcend our normal understanding of space and time. Researchers are also investigating the quantum vacuum itself, that strange realm of virtual particles and quantum fluctuations that permeates all of space. Some theories suggest that the vacuum might have different phases or states, and that transitions between these states might allow for faster-than-light phenomena. The search for dark matter and dark energy, the mysterious substances that make up most of the universe, might also provide clues about faster-than-light travel. These substances interact with normal matter only through gravity, suggesting that they might operate according to different physical laws. If dark matter or dark energy could be harnessed, they might provide pathways to faster-than-light travel. Advances in our understanding of black holes have revealed that these exotic objects might serve as natural laboratories for testing the limits of physics. The extreme conditions near black holes, where space-time is severely curved and quantum effects are strong, might reveal new phenomena that could be relevant to faster-than-light travel. The study of Hawking radiation from black holes has shown that these objects might not be the one-way streets we once thought. Information can escape from black holes, though in highly scrambled form. This suggests that the relationship between information and space-time is more complex than we previously understood. Cosmological observations are revealing that the universe itself is expanding faster than light. While this doesn't allow for faster-than-light travel within space, it shows that space itself can expand at superluminal speeds. This has led to speculation about whether the expansion of space might be harnessed for faster-than-light travel. The search for extra dimensions, additional spatial dimensions beyond the three we experience, might also provide pathways to faster-than-light travel. If these dimensions exist, they might allow for shortcuts through higher dimensional space, similar to wormholes but potentially more accessible. String theory, which proposes that the fundamental constituents of reality are tiny vibrating strings rather than point particles, suggests that the universe might have many more dimensions than we observe. These extra dimensions might be compactified or hidden, but they might still be accessible under certain conditions. Advances in quantum computing are revealing new ways to process information that transcend classical limitations. While quantum computers can't perform faster than light calculations, they can solve certain problems exponentially faster than classical computers. This suggests that there might be computational shortcuts that don't require faster than light travel. The study of consciousness itself is revealing phenomena that seem to transcend normal spatial and temporal limitations. While these phenomena are controversial and not well understood, they suggest that consciousness might operate according to principles that are different from those governing matter and energy. Research into the nature of time itself is revealing that our understanding of temporal flow might be incomplete. Some theories suggest that time might be emergent rather than fundamental, arising from more basic processes. If time is emergent, then the speed of light limit might not be as absolute as we think. The search for a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics, might reveal new possibilities for faster-than-light travel. These theories suggest that space-time itself might be quantized, made up of discrete units rather than being continuous. This quantization might create loopholes that allow for faster-than-light phenomena. Perhaps most intriguingly, the search for answers is revealing that the universe is far stranger and more complex than we ever imagined. Each new discovery opens up new questions and new possibilities. The speed of light limit, which once seemed absolute and unbreakable, is now understood to be part of a rich tapestry of physical laws that might have exceptions, loopholes, and deeper structures that we're only beginning to understand. While we may never achieve faster-than-light travel in the conventional sense, the search for answers is expanding our understanding of reality in ways that are profound and transformative. Each new insight brings us closer to understanding the true nature of the universe and our place within it. As our journey through the impossible realm of faster-than-light travel draws to a close, we find ourselves confronting questions that transcend physics and venture into the deepest mysteries of existence itself. What does our exploration tell us about the nature of reality, consciousness, and our place in the cosmic order? What ultimate truths might be revealed by our attempt to outrun light itself? The first ultimate question that emerges is about the nature of limits themselves. Why does the universe have limits at all? The speed of light is just one of many fundamental constants that define the boundaries of what's possible. There's a maximum temperature, a minimum length, a quantum of action. These limits aren't arbitrary. They seem to be woven into the very fabric of reality. Perhaps limits are necessary for existence itself. Without boundaries, without constraints, there would be no structure, no differentiation, no meaning. The speed of light limit might be one of the cosmic parameters that makes the universe comprehensible and beautiful. It creates horizons that generate mystery, barriers that inspire creativity, and challenges that drive the evolution of consciousness. The second ultimate question concerns the relationship between consciousness and the physical universe. Our exploration has revealed that consciousness might be more fundamental than matter, that awareness might transcend the normal limitations of space and time. If consciousness can exist in the faster-than-light realm while matter cannot, what does this tell us about the true nature of mind and reality? Perhaps consciousness is the universe's way of understanding itself. The cosmos might be gradually awakening to its own existence through the development of conscious beings. The speed of light limit might be a necessary constraint that allows this awakening to occur in a coherent, meaningful way. Without this limit, consciousness might become fragmented and incoherent. The third ultimate question is about the purpose of existence itself. Why does the universe exist at all? Why is there something rather than nothing? Our exploration of faster-than-light travel has revealed that the universe seems to be structured in ways that preserve meaning, causality, and the possibility of understanding. This suggests that the universe might have an inherent purpose to create and sustain consciousness, meaning, and beauty. The speed of light limit might be one of the mechanisms by which the universe fulfills this purpose. It creates a framework within which consciousness can evolve, meaning can emerge, and beauty can be appreciated. Without this limit, the universe might be a chaotic, meaningless place where consciousness could never develop. The fourth ultimate question concerns the nature of time itself. Our journey has revealed that time is not the simple linear progression we experience in everyday life. It's a complex, multi-dimensional phenomenon that's intimately connected to space, matter, energy, and consciousness. The speed of light limit creates the arrow of time, the distinction between past and future, the possibility of causality. But perhaps time is more fundamental than we imagine. Perhaps consciousness itself is temporal, not just existing in time, but creating time through its observations and choices. The speed of light limit might be the mechanism by which consciousness creates temporal reality, weaving the fabric of space-time through its interactions with the physical world. The fifth ultimate question is about the nature of truth itself. Our exploration has revealed that truth might be more complex and multifaceted than we usually assume. In the faster-than-light realm, contradictory statements could be simultaneously true, reality could be observer-dependent, and the nature of existence could be fluid and paradoxical. This suggests that truth might not be a simple correspondence between statements and reality. Perhaps truth is relational, emergent, and contextual. The speed of light limit might be necessary to preserve a form of truth that's accessible to finite conscious beings like ourselves. 1. Saath. 1. The sixth ultimate question concerns the relationship between the possible and the actual. Our journey has shown that the universe allows us to contemplate impossible things, to imagine faster-than-light travel, to explore its implications, to push the boundaries of thought itself. But it prevents us from actualizing these impossibilities. Why does the universe allow us to think about things that cannot be? Perhaps the ability to contemplate the impossible is itself fundamental to consciousness. The universe might be designed to inspire wonder, to challenge our understanding, to drive us toward ever deeper questions. The speed of light limit creates a boundary that's absolute enough to maintain reality's coherence, but permeable enough to inspire our imagination. The seventh and final ultimate question is about the meaning of our existence in a universe with these constraints. We are conscious beings trapped below the speed of light, able to imagine faster-than-light travel, but unable to achieve it. What does this tell us about our purpose and significance? Perhaps our inability to exceed the speed of light is not a limitation, but a gift. It forces us to explore the rich complexity of the slower-than-light universe, to find meaning and beauty within the constraints of causality and temporal flow. It makes us co-creators with the universe, helping to weave the fabric of reality through our observations, choices, and consciousness. Our journey through the impossible realm of faster-than-light travel has revealed that the universe is far stranger, more beautiful, and more meaningful than we ever imagined. While we may never outrun light itself, we have discovered that the attempt to do so reveals profound truths about the nature of existence, consciousness, and reality itself. The speed of light limit is not just a barrier to be overcome. It's a fundamental feature of reality that makes consciousness, meaning, and beauty possible. It's the cosmic architecture that allows the universe to tell its story, to create meaning, and to awaken to its own existence through beings like us. And so we reach the end of our impossible journey. We've traveled faster than light through the realm of pure imagination. We've explored the paradoxes of causality, the mysteries of consciousness, and the deepest questions of existence itself. Perhaps you've discovered that the universe's speed limit isn't a barrier at all. It's the foundation that makes reality possible, beautiful, and meaningful. It's the cosmic architecture that allows consciousness to exist and wonder to flourish. Speaking of which, I realize I've been talking for quite a while now about impossible physics. If you're still awake, you might want to check if you've developed any unusual side effects, like spontaneous time dilation, the ability to perceive tachyons, or an overwhelming urge to explain relativity to household pets. Before you drift off to sleep, let me ask, what impossible thing would you most like to explore next? Thank you for joining me on this journey through the impossible. If you enjoyed this gentle exploration of faster-than-light travel, please consider liking this video. Your support helps me continue creating these quiet moments of wonder and discovery. May your dreams be filled with the impossible, and may you always find beauty in the boundaries that make existence possible. Until next time, rest well.